find it confusing, but in Japanese. Anyway, so coin selection, what it is and how it works in Bitcoin Core. And interestingly enough, in the latest version of Bitcoin Core, which was released yesterday, we have changed, they have changed the coin selection algorithm for, I think, the first time since a long time. So we're using something with some more scientific rigor behind it now, which is good news. Anyway, so of course this is not working. Hang on. Okay, so the concept behind coin selection first. So we receive Bitcoin in transactions. You've heard this before, I'm sure. And the Bitcoins that we hold, we refer to them as using outpoints. And an outpoint is just the ID of a transaction somewhere plus an index inside of that transaction. And this is the index of the outputs, which refers to the outpoint which we own. It's convoluted, but so basically you have a transaction with two outputs. The first one is yours. The second one is someone else's. So you have a outpoint which says the transaction ID and index 0, because you have the first one. Now, important to note is that you never ever have the same outpoint for two separate UTXOs. So even if someone sends you money for some odd reason, in a single transaction sends you money twice to the same address. So like output first is to address ABC, and output second is to address ABC. You still have a distinction between these two outpoints because the first one has index 0 and the second one has index 1. Right. So when we think about the balance in our wallets, what we're actually talking about is the sum of all of our outputs, the sum of all of our UTXOs, the coins that we have not spent. So when we're sending someone coins, we have to do exactly the same way that we do when we pay money at a store using cash. That is, if we're paying $4.99, we can't just magically produce $4.99. We have to find coins, and usually we just give them a 5. And then they give us back a 0.01. So we get back 1 cent, and we pay them $5, a $5 bill. And this is exactly the same process that we have to do here, because all of these outpoints, you can't split them up or spend half of them or spend a quarter of them. Either you spend them or you don't spend them. So in this case, you have to find a good selection of coins, or in the sense of like $7, you find a $5 bill and two $1 bills. That's a great case for paying $7. But if you don't have a $5 bill and two $1 bills, you may have to pay a 20 and get back up. More than you're paying, you get back. This is the same case with coin selection in Bitcoin. So we have to pick enough coins to cover, and then we have to send back the change to ourselves as a new coin. So we actually create a new coin for ourselves. This is our change. And then we send the rest to the person who we're sending to, and we keep a little for the fee. So now, this is a little naive, and there are actually better heuristics than this, but it's a good starting point. So we want to minimize the number of coins that we spend. And this is good for several reasons. So whenever we use several coins at the same time, we're telling the entire world that this coin and this coin and this coin, they belong to the same person. We're not telling them who that person is, unless they know who is paying money to whom. But if I'm paying you money and I use 3 UTXOs, and one of them happens to be connected to a bank robbery or something, then you can connect that to me. which is probably good for the police, but bad for me. Another reason why this finding as few coins as possible is a good reason is because whenever you add coins, you have to sign the coins. You have to you have to prove that you own them. And you do this using signatures that you attach to your transaction. And that means transaction grows in size. And because it grows in size, you have to pay more because you're paying the fees paid per byte of transaction size. So the smaller your transaction is, the cheaper it is to send for you. So this is also a matter of just economic gaining a few satoshis or however much it is. Right, so there are several heuristics, as I said before. One heuristic is to find, let me see here. Right, so if we can find enough coins to exactly cover the amount we're sending, we don't even have to include a change to ourselves. Like I'm paying a $5 bill to pay $5, and then I don't need to get anything back. That means our transaction is smaller, and that means it's also a little cheaper. Anyway, this whole process is called coin selection, and a lot changed, as I said, with 0.17. So there's a new algorithm called branch and bound, also known as Murch's algorithm, because the guy who made it his name is called Murch. And then there's also the old algorithm called knapsack solver, and that's still used as a fallback right now, but it's probably going to go away completely in a future version. There's also something where coins with the same destination are grouped together. This is an optional feature that you can turn on if you want, and you probably should. So basically what this does is if you have someone sending you money to the same address more than once, then this is obviously a privacy problem, because if you spend partially, like one of those UTXOs together with 10 other coins, and then you spend another one of those together with 10 other coins, then you've told the world that these 20 coins all belong to the same person. Because people can just see, okay, he's spending he's spending with the same pub key twice. That means it is the same person. So what you want to do is you want to always spend these coins together or not at all. So if you have 3 coins all belonging to the address ABC, then you want to either spend all 3 coins in one go, or you want to not spend them at all. And by turning on the grouping feature, which is in 0.17, it will automatically do that for you. So I'll talk a little bit about the knapsack solver first, which is the old one. The idea behind the knapsack solver is, let's just brute force the thing, and that's that. That's it. So we randomize, good stuff. Well, randomize is actually good for privacy too, so we want to do that always. So we randomize all our coins that we have available, and then we try a bunch of times. And every time we try, we see, oh, how good was this one? Well, we're paying less in fee or whatever, so this is great. And then we try again, and we try again, and we try again, and we keep doing this. And for big wallets, this is a little intensive, but that's what we've been using up until 0.16. So this is what you've probably been using so far. So if you go into a little more detail, you will, okay, so first you shuffle the coins, you randomize them, and then you go over them. And so there's a number of cases here. So one case is the value of that, the coin, the UTXO, is exactly the value that you're looking for. In this case, you will immediately just stop and just give that back. You just use that. Because that will give you no change output, just one single coin that's very small. And it's just ideal in every case, so you just pick that always. But if that's not the case, we move on and look at the coin value. If it's less than what we're looking for, if it's less than the target, we will add it to a set in the value list, sorry. And then we just keep track of how much we've added to the value list. So we're tracking all of the sum of all of the coins that have a worth less than the target. And finally, if it's more than the target, and it's smaller than whatever other coin you found that was larger than the target, then we mark this as the smallest higher. So what we're basically essentially trying to do here is we're trying to find a coin that is as close to the target as possible, but higher. Right, so at the end, if we now have the target as the sum of all of the total, then we just send everything back, the value list. And if it's less and there's a marked coin, then we send the marked coin back. So here, the less part is like, even if we took every single coin that we have that is smaller than the target, we still will not be able to get to the amount that we need. So we might as well just use the one that was closer to the target, as close to the target as possible. So that's how knapsack solver works. A little more details about the selection here. So we get the value list and we sort it in reverse order. So we had the most valuable one first. And then we approximate the best subset. We go into this in the next slide. And then we return either if you had a good solution, or if you don't have one, we return the marked coin. If you don't have a marked coin, then we fail. Like we can't fulfill this. Someone is trying to send 10 Bitcoin, but they only have 9, or something like that. So the approximation part, let me see here. Yeah, okay, so like I said, we keep repeating over and over again. In this case, we repeat 1,000 times. So what we do is, and I told you this is very brute forcey, but we go through the coins twice. So the first time we go through the coins, we toss a die. We toss a coin, actually. And if we get heads, we add that output. And we keep doing that. And every time we add a coin, we check, are we at the target or above the target? Then we check if we're better than the best that we have so far. So after we go through the random time, we go through again, and we just add everything that's not added anymore, and we check again. So we keep doing this a bunch of times, and we just keep the one that is the least wasteful. So all the things that I mentioned right now is actually done about 7 times with different parameters. And this is all like you try to minimize the number of coins with a long unconfirmed chain, or you want to use only confirmed coins, or you want to use as trusted coins as possible. For example, it will try to use coins that are confirmed rather than using coins that are unconfirmed and stuff like that. So it does these various iterations of the same thing. So branch and bound is a little more sophisticated and a little more efficient. So the idea here is to right, so the idea here is to use effective values per UTXO and efficient search for the exact matches. So effective values is, so the idea here is that when you're sending coins, not only are you spending the coins and getting money back, but you're also going to, at some point in the future, spend the coins that you're sending back to yourself. So what you want to do is you want to see what the long-term versus short-term fees are for these coins, because that means you can make a better prediction of how wasteful spending something is. You may have a coin that will actually be dust in the future, or you may have spending a coin will actually cost you money. And then we use, instead of doing this whole repeat a bunch of times, you just do this depth-first exhaustive search, well, sort of exhaustive. And we just have a waste metric, and we try to just minimize that. So it's very straightforward. What you do is you have, okay, so like I said, we have long and short-term fee rates. So we have the long-term fee rate, and this is the minimum fee rate of like 1,000 blocks in the future. Like I was asked of spending a change output, a resulting change output, and you can use that to figure out what the effective value is for each of these UTXOs. And that's just basically the effective value, no, the value minus the fees, basically. So you just ignore all the inputs that have a non-positive effective value because they will actually cost you money if you spend them or if you use them. And you then calculate the amount available. You just go through all of the UTXOs and just tally them up. And if you don't have the target, you obviously fail. And then you sort the UTXO pool in descending order. And this is, knapsack solver. What we want to find here is we want to find an approximate exhaustive result. So we don't want the wallet to spend like 10 hours to go through all of their billion UTXOs just to find that extra Satoshi. That doesn't seem very profitable. Probably pay more in energy for the computation. So this is the overall algorithm. There are three outcomes, I guess, or three subroutines in this thing. So the one is called this backtrack and record and iterate. So we backtrack if we run into any of these conditions. For example, we ran out of coins, so we can't actually get to the target anymore. Then we backtrack because we can't find a solution. Also, if the selected value is out of range, which means if it's way too high, or if we're more wasteful already than the best solution, because as we iterate, we add more waste. So we can't remove waste by adding a coin. We will always add waste. So if we're more wasteful than the best solution, we just stop and backtrack. So if we're within the range of target, meaning we have less than the target, we record, and after doing that, we backtrack. And finally, if we're not backtracking, we iterate. So backtracking. Backtracking is, so we have this, I said a binary tree. What it actually is, it's a Boolean vector that we add true or false to. So a true means it's enabled, and a false means it's not enabled. And this is for the UTXOs. So what we do is we just iterate through this from the end. We remove all the false entries that we have until we hit a true entry, or until we run out of entries. And now, if this is now empty, then we finished because we've tried everything. And if it's not empty, we just unset the last entry, and then we remove the values from the current value and the current waste. So we keep track of the value and the waste from the coins that we've added and removed in this. And if it's less than the best waste, we store this selection as the current best solution. So this is what we will end up returning when we finish iterating. And so finally, the iteration is when we're not backtracking and we're not recording, we're just moving to the next step, and we just add another entry to the list. And we just add a true, so we take the next UTXO, we remove the effective value from the available current value. This is, well, the available value, I mean. And this is just so we can track that if we're running out of, if we don't have enough to satisfy the target. And there's an optimization we can do. But basically then we just add to the current value and the current waste from this UTXO that we just added, and we just go loop again. So this is branch and bound. At the end, what we do is, well, if we don't have a selection that works at all, we just fail. Otherwise, we return it. But, I mean, as I said, we're storing this as a list of Booleans, so what we have to do is actually find and pull out the UTXOs and add them to a vector and return. It's a minor detail, but yeah, so that's how branch and bound works. So there's some references. If you want to read the paper, you can do that. Yeah, thank you. Oh, questions, by the way. Yeah.
What are your thoughts on coin selection for UTXOs that have very small values that are not going to be economical for a while? Like a long time ago, one of those Sochi Olympic guys sent
Well, I think I think that UTXOs can be useful even if they're not economical. For example, if someone hard forks without a repro protection, you could use them to separate between the two forks, for example. So even a zero value output could be used in some ways. You could also have other uses for UTXOs that we haven't thought about yet. So I don't know. I wouldn't say that we should delete UTXOs because that's going to start a big. Well, should we delete these? These are really small. We should delete them too. And you never know. Like one Satoshi may in the future become actually 1,000 millisatoshi, which it already is. But I mean, we could. It may be possible that one Bitcoin is worth like $1 billion. So we want to have to just make one Satoshi actually divisible, and then we suddenly have 1 million Satoshi, or 1/1,000,000th of a Satoshi being worth something, and then these one Satoshi outputs actually are used for something. So I mean, I don't know. I don't think we should remove anything from the UTXO set.
What makes the waste method that you mentioned to optimize against? Why not choose another method? The way I see it, coin selection is a problem also choosing what's the best method to optimize.
Or would there be a reason to use another metric instead of this waste for certain wallets or certain situations? What makes this good? Where is it bad? Stuff like that. Right. So, I mean, branch and bound is optimized for people who want to just use a wallet normally. So if you're on exchange with like a ton of UTXOs and you don't care about privacy, for example, because you're like, we're just an exchange, we're open, like everyone has our deposit address, whatever, then branch and bound may not at all be what you want to use. You may have a completely different approach. And so this waste metric thing here is used for branch and bound, but there's also implementations, or not implementations, there's an algorithm which claims that you should create an change output that is approximately the same as the amount you're sending. And if you do that, what's going to happen is that after you've been sending for a while, you're going to find that you have less and less occasions where you have to find multiple coins, because usually if you send 0.1 Bitcoin, you're not going to suddenly send 1 million Bitcoin. But if you're sending 100,000 Bitcoin every time, you're not suddenly going to be sending a bunch of 0.01 Bitcoins. So there's it's a way to profile you as a user. I haven't seen that being pushed forward anywhere, but it's something that was recently, I would say a few months ago, that I saw a blog post on, so it was very interesting. I hope that answers your question. If anyone else has input, that would, Otherwise, thank you very much.
Okay, we'll continue with the next presentation by James. The audio isn't picking up. If you have any questions, you should probably approach closer to the front, and we'll hand you a mic so we have the recording of your question for later.
Hello? Okay, we're good. Hi, so my name's James Chang, and maybe a quick introduction about myself. So my contributions to Bitcoin have mostly been on the project LibBitcoin. So there I do documentation. I've been working my way up the repositories and APIs. I've written examples for LibBitcoin. I think it's a fantastic developer toolkit. And the lead maintainer, Eric Voskuil, who's speaking later today on Cryptonomics, asked me to do a introduction to the toolkit tomorrow. But I also volunteered to talk about HT wallets because I think it's a cool topic. So yeah, so HT wallets, there are basically three things I like to cover today. So the first is, when we talk about Bitcoin wallets, you always have some kind of secret or entropy that you want to keep safe. And so one way to store or handle it easier than just raw byte sequence is mnemonics, word lists. You guys have all used HD wallets. I'm sure you're familiar with that. The second part is you obviously want to derive new fresh keys whenever you have a new transaction, right? So that's the child derivation part. And thirdly is the hierarchical tree structure that you have. So we have some kind of standard way of deriving our keys, which really helps with recoverability of wallets as well. So I'll start with the first one. This is captured in bit 39, mnemonic keywords. And so what we're basically doing here is we have some kind of entropy of variable length that we want to encode in words, right? So here we have 128 bits, but you can have anything that's a multiple of 32 bits all the way up to 256. And the reason why you do that is because when we encode these into words, we want to make sure that we can have this like checksum part. So we have a 4-bit checksum. It's the first 4 bits of the SHA-256 of the entropy that you begin with. The length of the checksum depends on your entropy length, right? So when we concatenate the secret with the checksum, that has to be a multiple 11 bits. So all these 11 bits, as you see at the bottom, they ultimately map to, via dictionary, they map to words. So right here we have, for example, which, collapse, practice, ice, least. And there are different languages available. You can map your entropy to different language dictionaries. So what we've done so far is simply we've generated entropy, we've concatenated a checksum to make sure that if this, if this word list is mistyped or you mix up the words, that can be catched. And the resulting word list essentially encodes the entropy. So that's part one. Then we would like to create let's say a root secret for a wallet from this word list, right? You can imagine yourself backing up your HG wallet from this word list. And what we do here, and it's important to note that this is not just a reverse process from before. So what we're doing here is we're taking that mnemonic sentence and we're passing that through a password-based key derivation function. So that's quite a mouthful. So basically what we're doing there is it's an HMAC function, so you have a key and a message, and we do that 2,048 times to kind of make the brute forcing of that a little more expensive. And what we end up with is a 512-bit seed, and just so that I can make that clear, if we go back, that 512-bit seed is not the secret entropy that we began with. It is derived from that. So what you could do is you could figure out your own way of creating a word sentence, and as long as the checksum goes through, this derivation of that 512 bits would be valid. Does that make sense? Any questions? Pretty straightforward, right? Cool. Okay, so I can actually demonstrate that in a example here. So what I'm showing here is this is the Bitcoin Explorer. That's a command line tool. I'll go over that in detail tomorrow. But what I wanted to emphasize here is just the process. So we generate entropy, and we can create a word list encoded from that entropy. So here I can then create the 512 bits entropy with which I seed my HD wallet. Important kind of seeds the entire HD wallet. And the next part of HD wallets is captured in bit 32. It's around deriving child keys. So I'll go into the details of these keys in the next step. But basically what we're trying to do here is we're trying to generate new keys that lead to new addresses, right? So maybe I'm receiving multiple payments, and I want these payments to go to different addresses. Obviously, if they all go to the same address, then through chain analysis, it's pretty obvious that that's one person controlling. All these payments are going to one person. If I can generate fresh keys, then at the very least, chain analysis becomes a little harder. You have to infer certain wallet heuristics to kind of group these different addresses together. So as you see here, the way the derivation kind of works on a high level, you can derive via an index. So I have my master keys on the top left, and my child keys of the subsequent generation, they are derived with an index, so 0, 1, and 2. And those, from those, we can derive grandchildren with their respective indices as well. So we'll go into this a little deeper in terms of how the children are derived, but the point of having this ability is, for one, I can kind of create different subtrees, And every subtree, for example, could represent an account. It could represent a purpose. It could represent even a coin type or network. And that is standardized in a scheme that we'll see later. But basically, that's the advantage of being able to create these child tree structures with HD derivation. Okay. So the first thing we want to do is derive those master keys, right? So we have the 512 bits that we derived here. That seeds the entire HD wallet. And now we want to generate the master keys. How do we do that? So generating the master keys begins, again, with the root seed. As you can see here, it's valid entropy lengths go from 128 to 512 bits. So we generated 512 before, right? So that basically means you do not have to seed it with a mnemonic derived root seed. You can also seed it with your own 128-bit entropy if you'd like. And we pass that root seed into HMAC function, HMAC SHA-512, Bitcoin seed as the key, and the HG root seed as the message. And out comes 512 bits. And what we do now is we split those into left and right. So the left represents the master private key, and the right 256 bits, they represent the master chain code. So the master chain code, as we'll see later, it's an important piece of information because the master chain code gives you the, in quotes, privilege to derive, or the information required to derive children later on. So obviously from the private key on the left side, we can generate the public key point simply by multiplying with the generator. Pretty straightforward. And there we have it. We have the master private key, we have the master public key, and we have this thing called the chain code that we're going to use in a second. So that's it. That's our master keys. Yep. Okay. So then we want to derive children from these master keys. And so this scheme applies to every generation of child derivation subsequently. And so we start out with the parent public key, the parent chain code, which was right here, the right 256 bits, and the child index, which we saw one step before that. So for every child, we use an index to derive that specific child. Again, we pass that through an HMAC function. Here, the parent chain code as the key. We concatenate the parent public key and the child index to get, again, 512 bits, left and right. We split it up in left and right. The right side, again, as you can see down there, that represents the child chain code now. The left 256 child index, and we've derived both private and public children key from this scheme. Does that make sense? No questions? Okay. So there's something that we can observe here. So here we've required, okay, if we look at the keys we've taken to derive the children, the parent keys, in effect, we need the parent private key, right? The parent public key on the top left, I could derive from the parent private key. So as this scheme stands right now, I need the parent private keys to derive any children. But if I observe at the bottom left where we have, in brackets, the parent private key plus left 256 bits times the generator, I can write it out like that. So what I have now is essentially the parent public key plus the point of the left 256 bits, right? And what that equals is that I can essentially skip the step where I take the parent private key and derive the child public key directly from the parent public key. Yeah? Cool. I'll go over that one more time. So this is derivation with the parent public key and parent private key. I can skip the step with the private key because if I multiply that expression out at the bottom, that is essentially the parent public key plus the point of the left 256 bits. Okay, so we can derive children from the private key, but we can also derive public children from the parent public key. And to make that a little more obvious, here is like the derivation path. So we have the parent keys on the left. We have the private key and the chain code. Obviously, from the private key, I can derive the public key. But in terms of the children, I can now derive the private children in the arrows as you see with the according index. And from the children private key, I can then derive obviously their public counterpart. And what we saw before is, with a bit of algebraic trickery, we can directly derive children public keys from the parent public keys, as you see in the orange derivation paths right now. So that's pretty nice. So that gives us a certain property where we can create two parallel derivation paths, right? I can derive everything via the parent private key path, but I can also take a public key, extended public key, and start deriving children of that public key without actually revealing any private keys, right? So for example, if you have some front-end application where you wanted to regenerate new addresses, you can allow to do that with a extended public key without revealing or exposing any private key information. Okay, and then there's a encoding design or format for extended keys, both private and public. There's one interesting thing about that where we have a parent fingerprint. So whenever we look at one of these keys, one of these squares or boxes, they all include a parent fingerprint, a hash 160 of the private key or the parent public key. And so that allows you to look at a child and say, okay, does this child actually belong to that parent? That's just a kind of checksum-ish verification feature. So we have the chain code in there. We have the private or public key. If it's a private key, sorry, if it's a private key, it's 32 bytes. But what we do is we just pad it with a 0 byte. You have version, depending on whether it's a mainnet or testnet network, or whether we're talking about extended private key or an extended public key, right? So you have a checksum as well, and we end up with 82 bytes. So an extended private or public key is 82 bytes, includes all the information you need to derive the respective children. There we go. So I also have an example on that. So here we go. So here we're deriving the master keys as we've shown before. We can have a quick look at the extended key serialization. It starts with TPRV, PRV for private, T for testnet, because I'm using the testnet version there. And from that, I can derive the equivalent extended public key. This begins with tpub, testnet, public key. And here we can see how we would derive the HT children. So here's an example. I'm taking the master private key, extended private key, and I'm deriving this key right here. And through the indexing, you can see the indexes we use for that derivation path, 0, 1, and 2. And there you go. That is the respective child. Again, with the same beginning T, PRV, T for testnet, PRV for private extended key. Okay. So this is pretty interesting. That's all fine and good. What can happen, however, is if the parent extended publicly and the private child is exposed, namely what you see in orange right now, there is the possibility of deriving the parent private key. So in a sense, that's kind of like an upstream key exposure. We have perhaps, you might have this front end that just works with the extended public key, but for some reason, a child downstream private key has been exposed. And so this is what can happen. Because the child private key essentially was the scalar addition of the parent private key and the left 256 bits, we can now reverse that operation, right? So we can now derive the parent private key by subtracting the left 256 bits from the child private key. And what's happened now is the parent private key has been exposed. Let's have an example on that. So just to show you that that actually works, and I'm not making this up. So here I've generated the parent keys, right? The parent private key, the parent public key, the parent chain code, and the child compute the parent private key from that information, D tree. So we have the extended public keys. The parent public keys in orange on the left side are exposed. There is a private key, child private key, that is exposed. And the chain codes of both private and public key are the same, of the same index, right? Same for the children. There we go. And then we can derive the parent public keys. So what's happened now is the parent private key has been derived, and subsequently all the children downstream can be derived from that. So imagine the top left were, let's say, the master keys, right? If the master keys are exposed in that way, then obviously my entire wallet has just been exposed. So that's really bad. Fortunately, there's a way to limit that, and we do that via hardened HD children. Okay, so what we have here is the same derivation schematic we saw before. This is how you would derive a non-hardened child, right? So we have pub key, parent chain code, child index, parent private key, and so on and so forth. So we're going to change that a little bit. Have a look at the top left where we have the parent pub key. I'm going to change that pub key to a private key. Now it's highlighted in orange. What's fed into the HMAC is slightly altered. We concatenate the message with another 0 byte. And let's have a look at how that affects the factors downstream. So obviously the left 256 bits change. I've denoted that prime. The right 256 bits, which is the child chain code, are altered. And essentially the child private key and the child pub key are now hardened keys, hardened children keys, right? We refer to those as hardened keys. And so how does this help? Well, let's have a look at how the derivation looked like before. So I'm switching back to the original derivation on the top, and at the bottom we have the hardened children pub keys. So here you can see how they are no longer the same. It is no longer possible to derive a child pub key, a hardened child pub key, directly from the parent pub key. That is no longer possible. So we've broken that derivation path. It used to be possible to do that, right? I take a extended pub key, and I could just derive all the children from that. That has been broken with this schematic. The same goes for the right 256 bits. That has been altered with the scheme here. We've broken that with the hardened keys. And you can see in the children keys, that's noted with this like prime symbol, right? Okay, so I have an example for that as well, which I can show. So here we're trying to derive hardened key, index 44. And so this is the important part. So here I'm trying to derive a child pub key from a hardened parent pub key, right? Both denoted with prime. So I'm trying to derive a child pub key, a hardened child pub key from a hardened parent pub key. And that's not possible because we broke that derivation path with this scheme, right? Okay. Okay, so finally there is a standardization in terms of the derivation hierarchy captured in BIP 44, I think 43 as well. And so what that basically says is when you derive your keys for use in the HD wallet, there's a certain scheme that you adhere to. 44 prime just refers to for the BIP. 0 on the second index here refers to whether it's mainnet or testnet. The third one refers to the account number or change address. Okay, so this is obviously a nice standardization. One thing that it really helps out with is HD wallet restoration. So everything we've talked about is kind of recapped here, right? So we have the mnemonic word list and the optional passphrase from which we derive our master keys. We have the different accounts here, right? First testnet account, second testnet account, third testnet account. And let's assume you've lost your hardware wallet and you only have that you only have your mnemonic word list and the optional passphrase that you've backed up. So every wallet obviously has a unique usage pattern in that sense. Like the tree that is derived in your wallet will look different depending on how you use it. For every new receiving transaction, I'm going to generate a new receiving address. For every send transaction, most likely I'll generate a new change address. So how do I know when I'm restoring from scratch? How do I know which addresses I should drive up to, right? And the way that works is you basically just you check whether these addresses have been used or on the blockchain. And if they are unused, you just iterate through the indices. And if they are unused, you kind of tolerate a gap up to 20 unused addresses. And then after 20, you stop searching. You say, look, I've restored the address. I found a gap of 20 unused addresses. Likely, the user of that wallet never generated more than those. So to make that specific, we have one more example here as well. So here I'm taking a mnemonic that is in quotes backed up, and I am generating the children that we saw before, and I want to see which one have been used and which ones have not been used. And so what it is doing now is generating these addresses, and it is querying the server in terms of whether they've been used or not, right? So this one has been used, this one has been used, the third one has been used. So perhaps the user generated an address but never received funds on it. That could be possible. But then this one was used again. And after a gap of 20 has been discovered, it stops the search. So that's essentially how a HT wallet is then recovered from the mnemonic. And obviously the standardization of this hierarchy helps a lot with that. Okay, so that covers the chapters. Those are the three things: mnemonic word lists, child derivation, and standardization of the derivation hierarchy. Yeah. Do you guys have any questions? Be happy to try and answer.
Hi, I'm Jonathan Underwood with Bitbank, and I also work on Bitcoin JSLib. And one thing that we've found many, many times with the issues that we get from developers on our repositories is that I think the whole BIP39, BIP32, BIP44 combination, a lot of people feel like this solved wallet UX, but I feel like it really doesn't. And I think this can also be seen by, like, for instance, LND recently invented a new AZ kind of drop-in replacement for BIP39. Also, there's other proposals like BIP47 payment codes, which is kind of increasing the privacy aspects of kind of like what BIP32 couldn't really do, because everyone wants to exchange XPubs instead of addresses, but then, oh wait, there's that whole, you can recover the the parent private key, so you don't want a really big, wide area. So I think, what's the number one thing that you think could be improved upon this whole HD scheme that you've explained today?
Unfortunately, I'm
for change addresses and so forth, but rather using the non-hardened pub keys for receiving addresses. Is that
in the fashion that I described earlier? So in that sense, the parent keys in the accounts at the very least are protected, or at least hardened.
Right. So my understanding is, if you wanted the ability for someone to be able to send funds to your address without knowing without being given the address beforehand, then you can use an unhardened pub key.
Yep.
Right. And so you would use that for a class of transactions where, basically you use it for deposit addresses, for example.
Yeah, absolutely, absolutely.
But you would only use it for deposit addresses.
Or change addresses, yeah.
Change addresses as well?
Yes, yes.
Okay.
Yes.
Okay, all right, thanks.
Yeah. So that's the 0 and 1, 0 for receiving, and then 1 for change addresses. Yeah. Okay, thanks guys.
Okay, continuing on to Ryan's presentation. Does anybody need a 5-minute break? Show of hands if you need a quick 5-minute break. 5分休憩の必要な方. All right, let's take a quick one for 5 minutes. And continue on 2:30. 2時半からまたスタートします。
How many satoshis for air conditioning?
Okay, if you also want to grab a quick coffee, you can go to the ninja room. またコーヒー必要な方は忍者部屋に行ってください。
What did I do?
What is all this? It's so weird.
Test. I think I pressed something on it.
Yeah, I don't know.
All right, we got one over there.
What's the translated version? There you go. Alright.
All right, so I'm now going to talk about Bitcoin wallet security. And I was also asked to talk about key management and hardware security modules and a bunch of other topics all in one talk. This is going to be a bit broader than some of the other talks because this is a kind of an important subject about how do you actually store Bitcoin and then some of the developments around the actual storage of Bitcoin in a secure way. Some that have been integrated into Bitcoin Core, some that have not, things like that. Who am I? We went over this. If you don't remember me, tough. So I was previously working at LedgerX. I was their Bitcoin developer, and LedgerX is a CFTC-regulated Bitcoin options exchange and clearinghouse. So they have to actually take possession of the Bitcoin that are used for the options trades and store them long-term, and the Bitcoin absolutely must be there for the settlements and the withdrawals that eventually occur. If they're not, then the whole idea of a clearinghouse, what's the point? So just some really brief lessons learned here. So when you have a security situation that is just really has to be done right, automation is really useful to make sure that everything works and everything is right, get it tested. It's great to have automation, then you don't have to do it anymore. But there's actually a high cost to doing automation. And sometimes for high security situations, maybe automation isn't the right option. So that was one of the lessons that I came away with. Also, there's actually no end-to-end off-the-shelf storage custody Bitcoin solution for institutions, really. It's not just use Bitcoin Core and you're good to go. You have to actually, if you have people in your organization that don't know how to use Bitcoin, they have to be trained to use Bitcoin and things like that. And just download Bitcoin Core isn't sufficient instructions for normies. And then also, if you're working with regulators to get a license exchange, for example, then be careful what you tell regulators because some of those will be interpreted as promises or design specifications, and then that puts further constraints on the actual shape or structure of what you can actually build. So as an example, one of the consequences of certain representations that were made to regulators, that they were not wrong representations, but as a consequence of them, though, I had to write a lot of custom wallet software that didn't previously exist. And honestly, I mean, the hardware integration for Bitcoin Core is still in development and forthcoming, so it's not like there's ready-made solutions anyway. So when we talk about storing Bitcoin, some of this is going to be a little obvious to the old-timers here, but in case you're not aware, you can have things such as hot wallet versus cold wallet, and then you can also have different ways of storing the keys for your wallets, most notably online or offline. Some companies that store Bitcoin on behalf of users have chosen to use hot wallets, which is basically press a button and you can steal the Bitcoin. And then others have chosen to do offline storage. So offline storage can work in a number of different ways. One is that you can have something as trivial as writing down your seed on a piece of paper and only loading it up onto a computer that is air-gapped and never connected to the internet, to other things where you perhaps have it stored on a computer or a hardware device that is never connected to the internet, but it's not on paper. Some people will find it ironic that one of the major suggestions used to be for Bitcoin users that if you're storing Bitcoin, store it on a paper wallet and put it in a vault. And this is contrasted to the fact that Bitcoin is very software intensive, so the fact that paper was a major recommendation was a bit ironic. Okay, and then there's also specialty purpose-specific devices such as hardware wallets and hardware security modules, which I'll talk about more later. And then
there's also certain groups of people that have decided to like build bunkers underground and hire security forces to protect Bitcoin and for long-term storage. And you know, in some cases, it's really interesting because software can sometimes provide a lot of the advantages that hardware could provide or that armed security forces could provide if you're just smarter about how you do it in software. So there's a bunch of different areas to explore here. I was actually giving a custody talk at Baltic Honey Badger recently in Latvia. And you know, one of the important things to ask though is like, what is the actually appropriate level of security for different use cases? Not everyone needs that armed security forces, or not everyone needs to you know, use Shamir secret sharing to back up multiple keys or whatever and pass them on to like your heirs and whoever owns your estate when you die. And then other people do feel that's appropriate. So it's good to be aware of the different spectrum and different options available for storing your Bitcoin. And in particular, the reason why I mentioned heirs is that in the event of your death, you know, if you want people in your family to be able to access your Bitcoin, or in the event of a company that has business continuity interruptions, the instructions need to be extremely clear and very, very well tested. Speaking of testing, I mean, many people don't realize this, but anytime you're doing anything in Bitcoin, including transactions or long-term cold storage or whatever it is you want to do, you can always test on RegTest first. Anytime I spend Bitcoin, I try to test a transaction on RegTest first in an environment that I control to verify that my steps are actually correct. I think everyone should be doing that, even though I recognize it's a lot of for using your Bitcoin, or you know, if you're advising a company, you know, how are they using and accessing their Bitcoin? There needs to be actual steps documented. So for certain scenarios in companies or even individually, the way I like to think about it is something called the signing ritual or signing ceremonies. And this is usually where you have a dedicated room or different rooms in different buildings around the world that are specifically constructed for signing Bitcoin transactions. I'm about to give an example actually on the next slide. Is the DNSSEC signing ceremony. Is probably the most public and most transparent one. It's definitely inspirational and probably the most entertaining video on the internet. It's 4 hours of people reading off checklists. It's really entertaining. But no, it's a great example though. I think it's kind of interesting that there isn't one for this for anyone doing their Bitcoin rituals. Like no one has done a transparency video about how they actually store their coins or withdraw them. I think that's really interesting. Another idea that was mentioned to me just today was the idea with a signing ritual. It would be interesting to try and considering a situation where instead of having software sign your transactions, consider doing it by hand. I think the computationally feasible step in there is manually hashing everything. I think that if you use a computer for that step, you might be able to get away with actually manually signing transactions, in which case you might not need computers to touch it, and then you can get away with not having to check for malware on any of your devices. Okay, so if you were to actually design a signing ritual, what would actually go into that? How would that actually look? So hardware wallets are something on the market. There's a few available. Something nice to have is that if you have a hardware wallet, which is a specialty device designed to store Bitcoin, screen on the device would be really useful, because then whenever you're about to perform some action, the device can tell you what it thinks you're about to do, period. The idea of unlocking a hardware wallet, it actually kind of terrifies me. This idea of like a locked mode and an unlocked mode just seems kind of wrong, because the idea of security is that you want the security to always be on, not just like enable security and disable security while you're doing stuff. But have lots of backups. That's a good idea. One of the nice to haves that everyone has been talking about for a long time, but it hasn't been made yet. Maybe one of you can do it. Is the idea of running a Bitcoin Core node on a hardware wallet of some kind, and so that the consensus rules can be verified in the hardware wallet. There's an upcoming slide where I discuss this as useful for a Lightning Network, for example, where you can have a Lightning node running such that transactions are only signed in the event that they positively increase your balance or something. And and then the hardware device would be able to verify those rules and monitor blockchain data to confirm that. So there's another sector of the market that has been called hardware security modules, and this has existed long before Bitcoin hardware wallets and Bitcoin itself. And I actually think that the idea of separating hardware wallets and hardware security modules is actually a bit antiquated, and we shouldn't do it anymore. We should just call them all hardware wallets or call them all hardware security modules. But they're generally seen as having more computational power. But again, though, I mean, like from the perspective of selling equipment to people or providing equipment and security, does it really make sense to have like some customer demographic having better security or more features than others? Like we all have the same requirements for the most part for securing our Bitcoin. So I'm not really sure that fragmenting the market makes sense. Okay, so I've already talked about this use case for Lightning. For hardware wallets that only sign transactions that positively increase the balance of the user. This would be useful for like hot wallets that are online but still using hardware security features. Another idea is that you can have a hardware wallet that is itself protected by several other hardware devices, not necessarily hardware wallets. But in particular, you can imagine a scenario where you use multi-sig on a cryptography level, not on the Bitcoin level, to gate access to a hardware device. So you have to have a quorum available in order to activate the HSM. One of the advantages of this actually is that if you have a number of people that you have entrusted to participate in this process, and perhaps they become irresponsible or unavailable, you could replace them without actually having to rotate your keys on the blockchain. Oh man, key rotation. I haven't even talked about key rotation. In theory, everyone should be rotating their keys quite regularly because you never know when someone has stolen your private key. And key rotation on the Bitcoin blockchain side has a cost. It has a fee associated with it. But if you have this multi-sig quorum stuff going on to access your Bitcoin or control it, then this is one way of minimizing costs while also improving your security situation. Okay, so now let's get down to like Bitcoin specific stuff. I think there's actually a talk right after mine about partially assigned Bitcoin transactions. So anyway, the idea of this is that you can have a standardized serialization format to communicate with hardware wallets. I don't want to steal anyone's thunder, so I'm just going to skip the rest of that. Another way, another thing to consider for hardware wallets is pre-signed transactions. If you consider that there's a high cost to actually accessing a hardware wallet or using it regularly, then one interesting thing that you can do is you can pre-sign transactions that are valid that you perhaps store somewhere else or encrypt them somewhere else, and you keep the decryption keys wherever. And then in the event of like an emergency or some other situation, perhaps you lose your keys or access to your keys or your hardware wallet, you can you can broadcast these pre-signed transactions. There was also a proposal a while back. Apparently this was actually not proposed by Bob. Bob informed me that it was not his idea. But anyway, if you wanted to have something like a vault, one idea that has been proposed is using a covenant, but Bitcoin doesn't have covenants yet, or at least we certainly hope it doesn't, and I don't think anyone knows whether it really does right now. But anyway, what you can do though is with time lock transactions, you always have this concern that perhaps someone could steal the key that signed the time lock transaction and instead sign a transaction that does not have time lock. So what you can do instead is send it to a pub key, and then, well, before you do that, you can sign a transaction that spins from this pub key that you've invented. And then you can delete the transaction that delete the private key once a transaction spins to it. And this is a way to make it a permanent time lock that must be exhausted before the Bitcoin can be spent. So this is an interesting thing you can add to any way of storing Bitcoin to improve security. Also, I am assisting with a custody workshop that will be occurring in San Francisco sometime in November. It's smartcustody.com, ran by Christopher Allen and a few others. It's just a one-day workshop for family offices. So what would be really nice if there was some sort of toolkit for how to store Bitcoin in a really rigorous fashion where you can also share documentation and like video documentation with other people about how to actually participate and use this and actually have like training and so on. One of the interesting things about BIP32 that was briefly mentioned in the last talk is that when you have the public keys, you can derive more public keys and more addresses without actually having to go back to your private key. You don't have to do any computation with the private key after you get your public key. And this is really useful, and this actually minimizes the amount of times that you have to interact with your secure hardware elements. Using BIP32 and many of these hardware wallet solutions can be really useful. So speaking of keys, we've been talking about keys for hours today. Something to consider is that if you've never done it before, or even if you have, perhaps participate in like some key signing. Just ask around, maybe particularly in Slack would be a good way to do it. If you have a PGP key that has or has not been signed before, I'm sure there are many people here, including myself, who would be happy to sign it. And there's some documentation at the link for how this usually goes. But this is useful for a web of trust. And that's all I have. Thank you. Any questions? I actually have not evaluated Casa HODL's solutions yet, but I think they released a Lightning node, hardware Lightning node, yeah. I assume it might work, maybe.
I have a question about when you were working at LedgerX, you were speaking about XPubs and like extended public keys and deriving keys and stuff like that. What do you think about the security of those XPubs? Like for instance, if we had a super secure private key and then we took the XPub and put it on the server to automatically generate addresses for users to deposit in, and someone hacked our server and put their XPub there, you know, that kind of defeats the whole purpose. So what do you think about securing the online XPubs?
Well, so there's some interesting things that you can do here. More specifically, there have been situations where exchanges have been hacked and deposit addresses have been switched out to the attacker's deposit address. Kraken and at least one other exchange uses PGP signed email receipts. And I don't know if Kraken does this specifically for deposit addresses, but the idea is that if you request a deposit address, they should email you something instead of going through the web, because most attackers would assume that they should just compromise the website and not also email. And there's a few other reasons for that, but also it's like PGP signed email as well, so that you can verify that it was actually sent by them. But then you could say, well, what if the attacker compromises their email sending component as well? I mean, one trivial thing that you could do is just communicate to them over another channel in the beginning and pre-commit to saying these are our Bitcoin addresses. Then there are also multi-sig things you can do where some Bitcoin exchanges are trying to not have custody, so they try to get the users to like have like an escrow participant in a multi-sig setup. And then you can do things like 202 multi-sig or something, and the escrow agent has to sign off on the transaction or whatever. And then then the escrow agent is an additional check on whether the address is correct or something. Yeah, things like that can improve the situation.
Okay, thank you.
All right, thanks.
Hi. So I'd like to follow up Brian's talk. He briefly mentioned this, but I can go in depth of what partially signed Bitcoin transactions is, what it gives us, and kind of the things people are working on to put it into practice. So there's history, motivation, kind of background of why this is important, what these things are actually doing, like wallet software is actually doing, and then going into the nitty-gritty of PSBT itself. As well as an example, I'll do a live example, doing it live, and then some resources. So historically, these partially signed transactions have had no standard format. Armory has its own format for a long time. Bitcoin Core has its own, just uses network serialized unsigned transactions, basically. These are incomplete, and all the APIs are completely different, and it ensures fragmentation. And there's also all these weird corner cases, like for segregated witness, a transaction to a legacy node looks like a zero input transaction. This is a way to basically flag it as a segregated witness transaction. But this sometimes gets the software, even SegWit wallet software, gets confused and then thinks it's a legacy transaction with zero inputs or vice versa. So there has to be a better way of allowing zero input transactions when you're building a transaction, especially interactively with other parties, making sure that goes smoothly and is not getting confused. This incongruity also just increases the workload for developers to support various things, such as hardware wallets or what I call external signers, just a wallet that doesn't have the keys local. So a couple summers ago, we had an intern at Blockstream, Andrew Chow, who's also a Bitcoin Core developer. He had an interest in finally solving this problem. He maintains, he helps maintain Armory as well as work on Bitcoin Core. And over a couple of years, he got feedback on the format, and it finalized as BIP 174. And it's just been released in .17, Bitcoin Core version .17. It's all there, and Armory and various hardware wallets are also supporting it. So the CoinKite's cold wallet, I believe it's cold card wallet, uses basically just takes a PSBT file, signs it, and hands it back to the user. So they use that natively. And there's other libraries that are now have support for it, such as Rust Bitcoin and others. So let's just take a look at what this solves. So in general, if you're a hard transaction signing program, I hand you a transaction, ask you to sign. If you don't have any additional information, it's really hard to reason about what this transaction is, what it's doing, especially in low memory environments like a hardware wallet, right? A hardware wallet has no sense of the UTXO set, values. So it's, you know, one thing you tend to do, so like in Bitcoin Core previously, and Ledger wallets and Trezor, you had to feed either the previous transactions, so the previous output, the previous transactions for the inputs for the transaction, or at least the full output information for segregated witness inputs. I'll explain a little more about that later, but this additional input information. And besides that, the previous transactions is not even enough. For example, if you're signing a P2SH or pay to witness script hash, then the signer doesn't even necessarily know what the actual script is. It's a hash of a script, right? So it might not have any clue. The signer may also want to reason about the outputs. So Brian mentioned logic like, I'll sign anything that gives me more money. But how do you figure out what's your money, right? I could withhold information from you, trick you in certain ways, thinking you're getting money when you're not. And this is one attempt to help solve this. Also, you might need key path information. As far as I know, all hardware wallets, modern ones, they operate only using HD key paths. And you need to feed that to them. And all these details come together kind of as crucial for anything working remotely well. You have to, each signer has a different piece of software, maybe a different piece of hardware, and currently there's just no good solutions. So the custody solutions today are kind of haphazard and only work with one or maybe two kind of setups. So I'll go over a little bit over the fields that the partially signed Bitcoin transaction, PSBT, have. It's encoded in base64 and eventually finalize it. So put it all together and then make a valid transaction for the Bitcoin network. So there's a global types type of field, and currently there's only one, which is the unsigned transaction itself. It's the transaction without any script sig values in it. So script sig is blank, the witness field is blank, there's no signatures or witness data of any sort. These are all just kept blank. And then there's per input types that start at input, transaction input index 0 and move onwards. There's, for non-witness UTXOs, you have to include the entire transaction, because what you're doing is you're taking the entire transaction, getting the transaction ID, which is the hash of it, and then checking that it's actually the same, it matches with the previous, inputs, what's called prevout, it's the hash of the transaction, as well as the index of the output. So you want to say, okay, this claims it's 3 Bitcoin, I want to verify that's actually real, and this helps verify that. For a segregated witness UTXO, you can kind of work around a little bit and only give it the serialized output itself. So just part of the transaction. And this is due to the fact that signature hashes in segregated witness include value under the sig hash. So if I claim it's 3 Bitcoin, then when I'm signing it or when the hardware wallet wants to sign, it says, well, this is 3 Bitcoin, and verifiers will then check this. So if I lied to you and it's actually 4, then it'll be an invalid transaction, and that's okay. There's partial signatures, which there's the key. The key is the public key, and the value is the signature itself. So these will be stored up. So if it's a 2 of 3 multi-sig, up to, let's say, 3 signatures could be there, 1, 2, 3, from each signer. It's not finalized yet. There's a sig hash type, which is kind of an advisory thing. You can say, the default is sig hash all, hash the entire transaction, sign that. You can also do other things like sig hash single, sig hash anyone can pay, all these different flags, as other people have talked about already. The redeem script, which is to do with P2SH, it's the serialized script that is then recursively evaluated. There's the witness script, which is the last stack element in segregated witness transaction inputs. That is the script that you'll evaluate. There's BIP32 derivation paths for each input, and in a multisig, it can be any number of them. The key is the public key for the actual key itself. And then the value is the master fingerprint and an array of indexes that gets you there. So the master fingerprint is part of the extended public key that you were told about earlier. So it just lets you identify it without no cryptographic guarantees. It's kind of weak. It's just a, I think, 4-byte fingerprint. And then so this transaction is being passed around, being signed, getting partial signatures. Eventually, at some point, you'll have enough signatures. Let's say 2 of 3, you get 2 or 3. And then a finalizer role is where the software says, aha, you have enough. It can take all those script signatures, script sigs, and then make it finalized. Get rid of the partial signatures, stick it into the script sig. And same thing with script witness. So, and then there's also per output types. I talked about hardware wallets especially want to know things like change outputs, because if you have a hardware wallet and you say, I want to send 2 Bitcoin to this address, the transaction that's being shoved to the hardware wallet will actually have 2 outputs in general. One was going to this strange address you've never seen as a user, but that output is also given this HD path, HD key path, which then the wallet says, aha, That's right, that matches this output matches my key. I just won't show it to the user because I know it's my Bitcoin. So you also, for each output, you have things like redeem script, witness script, and bit32 derivation path. So you can calculate this per wallet basis. And then I'll just go through a list of, it's kind of a laundry list of RPC calls. I'll just unroll them here. So I would use a pointer, but I don't have a working pointer here. So there's the create step, which you can see with create PSBT, and a little bit down, wallet create funded PSBT, bit of a mouthful. So the create PSBT takes, it's sort of like the create raw transaction interface, except instead of making this kind of raw transaction serialized thing, it makes a PSBT. The wallet create funded PSBT is like fund raw transaction. It's the equivalent, basically. It's the one I tend to use. And once it's created, you can process it. So wallet process PSBT is something like where you hand it to another wallet, and if they know something about an input or an output, they can fill it out, and they can also optionally sign it and pass it on to the next person or the next machine. And then eventually, when you think it's all done, when all the partial signatures have become finalized, or are ready to be finalized, then you can call finalize PSBT. And you can do the optional extract, which is give me back the final network serialized transaction, the thing you'd actually submit to the network. Transactions, hand it to a wallet interface, a hardware wallet interface, where the hardware wallet signs as well, and pass it back. And the resources. Let's see if I can pull it up. Okay, so, oh my. Is that normal? Well, enjoy. So here I have, I set this up because it's fairly manual setting this up because you use the hardware wallet to get these addresses, then you import them. But this is in RegTest, so I do not have 50 Bitcoin. This is my Ledger wallet. See, sorry, there's tons, I wish I could point. RPC wallet equals Ledger wallet. So I'm asking my Ledger wallet, what do you think you have? Well, you have 50 at this. I wish I had lapel or something. Okay, and then I say, give me information about it, Ledger wallet. And my Ledger wallet, the data inside this wallet.dat file, which is called the Ledger wallet, it's not the hardware wallet, it's the actual stored keys and everything on my computer. It knows about the two pub keys. It's a 2 of 2 multisig, and it knows it owns one of them, and it knows other various information about it as well. Yeah, it's zoomed in. 1 second. It's not responding to this. Oh no. I just zoomed in more. It's not going back. Okay, I'll try. This is just a lot of information. Let's see, so I've got this. Now I want to create a PSBT. That's a 2 of 2 multisig. One is a wallet I called Core wallet. I have Core and Ledger. So I'm just going to create a funded transaction, wallet create funded PSBT. It's going to go to some address I just picked. I'm going to send 45, lock time 101, use watch only funds, and add bit32 derivation paths. So it gives me this. This is in base 64. And it has a fee and change output. 1 second. And you can inspect it. So there's this output thing, as I told you before. It's got it has one. This is the Ledger one. Ledger outputs, both of them. And then there's the input section, which knows things like it's a witness UTXO. It has a redeem script and a witness script. and then various other information, including the raw transaction itself, which isn't too interesting. And then what I'll do is take that, and I'll sign it. First, I have to plug this in. My ultra secret password 1234. Very secure. So first I enumerate I want to get a hold of these devices, and so Ledger has one here. It has two interfaces. One's like the, doesn't really matter. One's the keyboard interface, doesn't really matter. And then, whoops, I lost a hold of that. Let's grab it again. All right, so I said sign this transaction. It's now telling me about an output of 45. It is not telling me about my change output because the core wallet handed it the HD pass, and I just signed it. And here we go. Here's something slightly longer. And we can take a look at the decoded. So now we should have partial signatures. One partial signature, pub key, signature itself, but it's not complete, it hasn't been finalized. So what I want to do is wallet process this, and then finalize USBT. And it's complete. Now it's in hex as you know and love. And this can be sent off to the network, and you're done. So this is kind of a multi-sig using PSBT end-to-end example. And that is all I have. Questions?
Right. Okay. So thanks again for Greg. And the next session will be 1 hour long. So let's take a quick 10-minute break. And you can grab yourself some coffee. And yes, we'll see you in 10 minutes in 3:25 then. 10分の休憩取ります。また続きは3時25分からです。
Hello, 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 hello. I'm not sure. Yeah, okay. It seems to be okay.
Was that?
Is it too loud?
No, I don't think so.
Okay.
We can adjust later too.
Yeah, okay. So, whoa. Okay. If you can't hear me, raise your hand. Okay. Was that? Yeah. What? You're not hearing? Okay. All right. Okay. All right. So you guys, you warmed up for the first half of the day, and now we're going to talk about bulletproofs. Is there someone here who doesn't know what bulletproofs is? Great. Okay. So we should start with that. I will apologize in advance. I will not get to the end of this, all my slides today. Instead, what I will do is I'm going to take a top-down approach where we look at what bulletproofs is, what they solve, how they are helpful. Then we're going to look at how they work. And then we're just going to go all the way down in the rabbit hole and just go from there and up. So it will start very, very dark and then get brighter as we go. So the idea is that as you leave here, you're going to be like, yeah, I still don't know what bulletproofs are. But you're going to have the tools to figure it out. So that's kind of the goal here today. And as we go, I think it's kind of boring. I think you guys are pretty tired, and I'm pretty tired too, and my voice is dying. So things are not great. But what is great is that we are going to be doing some fun things here on the right-hand side, where I will actually do all of the proofs and stuff that we're doing. So we're going to do zero knowledge proofs, and we're going to actually do them for real, computation-wise. And we're going to see that these two expressions actually do match up, or don't. Or we make a fake transcript, and it actually works, stuff like that. So that's going to be fun, I think. Some of you may have installed this tool. It's called Aside. It's a tool that I wrote, actually, for the purpose of learning this stuff. So it's very, I'm told about this particular slide. So most of what I'm talking about today is based on Adam Gibson, also known as Waxwing. He made a fantastic From Zero Knowledge to Bulletproofs write-up, which is about 45 pages long. The Bulletproofs paper is also 45 pages long, which is kind of interesting. But anyway, he's going through how he learned about zero knowledge proofs, and he's kind of teaching you how to do it on the way. And I'm going to go through kind of how he saw this and kind of trying to wrap it up in how I see it. So you're going to see someone seeing someone doing something, namely bulletproofs. Anyway, so this is the agenda. As you can see, we're not going to get through all this today. We have 1 hour. But we're going to get through, I think, at least half of it. But in particular, because you guys already knew, you already learned about zero knowledge proofs in John Newberry's talk this morning. So some of the stuff that we're talking about here, you've already seen, and you've had it explained once. So I'm going to explain it again. So hopefully it will stick a little more. Anyway, so bulletproofs, top down. So bulletproofs address a particular problem. To get to that problem, we're going to take a few steps together here. So, so background here, fungibility is necessary for money. So fungibility is where I have a $1 bill and another $1 bill, and if these two were somehow worth different amounts of money, then the dollar would be worthless as a currency. It would not be useful as a money. And in the same way, if I have a UTXO and another UTXO of 1 Bitcoin, and this one is somehow worth less or more than this one, then that is a problem. And money must not work that way. This 1 Bitcoin must be equally valued to these other Bitcoin. So Bitcoin has a problem because it's not very private. In fact, it's one of the least private currencies that exist. And this is because the ledger is completely public. See, like I said, we can track coins and stuff. And if we de-anonymize users, we can say, oh, this is a guy who He has money from this drug dealer, right? Well, it sucks to be him, right? He's been doing dealings with a drug dealer. He deserves it, right? Well, the thing is, like, I give you a Bitcoin, or okay, I give you $1,000. No, I'll give you $10 worth of Bitcoin, right? And you're like, great. And you use this together with your $1,000 worth of Bitcoin to pay someone else $1,010, and suddenly you're screwed because you have now tied these two together, and you had no idea that I was previously buying from or selling to a drug dealer, right? So it's absolutely out of your control, and there's no way for you to look this up, right? So this is a real problem, and it's a problem for everyone, not just drug dealers. And one solution here is to use something called confidential transactions. And what they do is they hide the value. They don't hide the addresses, they just hide the value. So if I'm sending to someone, you don't know how much I'm sending. You just know I'm sending some amount, right? Why does that help? Well, it helps because the way that you can do analysis and de-anonymization on blockchain transactions is by looking at the values and seeing who's sending how much to whom and when and how. You can see, for example, if someone is spending a big chunk of money, sending a big chunk here and then sending a small amount here, you can be pretty sure that this big amount is the amount that is being paid and the small amount is this change going back. So you can link this change back to the same user, right? You can do all these kinds of things to tie people and addresses or UTXOs on the blockchain together. So the problem here, though, is that confidential transactions are freaking huge. Like several kilobytes huge. Like you would be spending 10 times more in fees to send a transaction on the Bitcoin network if you were using confidential transactions today. So the solution to this problem, well, one solution to this problem is bulletproofs. So what they do is they make these confidential transactions smaller. They also make them smaller if you aggregate them, which we'll get to a little. But aggregating basically means that you're doing coin joins or whatever. You are together with other people adding together your transactions, which makes it almost impossible to see who's sending to who because everyone is just mishmashing together with each other. But bulletproofs are, roughly, they're an optimization of another of a number of other people's work. And well, this is actually not technically new in bulletproofs, but they can also prove general arithmetic. They can prove general arithmetic circuits, which actually Boodle's work also can do, but bulletproofs can do that too, which is pretty cool. So we're not going to talk about that at all. So okay, so general idea is you replace something called the inner product argument to reduce the communication by about a factor of 3. And you're like, okay, what does that mean? Well, we'll get to that. But basically what it means is that we're cutting something into 1/3, and that is the optimization. We're making it 1/3 of its original size. So the Bootle guys had 3,000 kilobytes or 3,000 bytes, and then the bulletproof will be 1,000 bytes. That's all you need to know about that. So, but there's something called inner product argument, and we're going to talk about that perhaps in detail, depending how far you get. We also, there's it's a detailed thing, but we don't need to implement commitment opening algorithm in the verification circuit. And that all makes no sense at all right now. But basically, we're optimizing. We're making things simpler, and we have to do less. And this is what bulletproofs are. They're building on a 2016 paper by Bootle and others, and they're making it smaller, and they're making it so that you don't have to do commitment opening algorithm implementations. And there's some other stuff, some fancy multi-party stuff, like I said before, if you are 100 people, for every person you add, the bulletproof only grows logarithmically, so it only grows very little as you add more people. So for everyone involved in this coin join whatever, it actually is beneficial to have more people. You pay less money to be more secure, or to be more private, which is a pretty good privacy feature. And there's also some helpful specifics in the paper itself. They're talking about range proofs, for example, which is something that is an integral part of confidential transactions. We'll talk about that too. As you see, there's lots to cover here. Okay, so the general idea behind that, and by what I mean when I say that, I'm talking about Bootle, the 2016 paper by Bootle, and they're building on a 2009 paper by some other guy. And what they do is they take the communication complexity is from square root proportional to logarithmic. And the general idea behind that is the Peterson paper about Peterson commitments. If you don't know about Peterson commitments, and I'm probably public coin, we'll talk about what that is. Like I said, this is top-down, so there's lots of things that we're going to kind of have to figure out as we go. Right, so this, like I said, this gives a square root of the square root communication of the group element. So, okay, let's look at what proofs are. Summary here. They optimize confidential transactions, which is built on something called range proofs. And they actually optimize coin joins, like they grow less and less the more people you add to them. So after the 10th person costs less to add than the 9th person, and so on. And so both proofs are a significant advancement towards better fungibility in Bitcoin and privacy and a bunch of things. So generally, everyone is excited about this. So that's why they are being talked about so often. So before we get into the bottom part, we're going to go even further and go down to the cellar of the bottom part and talk about some math. Before that, though, like a small note, this is actually not hard. And maybe I'm easily scared. I don't know. But so there's a lot of things, right, here. Lots of things. And you're like, wow, that's a lot of things. There's no way I could understand all these things. Like, there's so many things, right? Like lots of variables, like alphas and omegas and sigmas, and you're like, wow, I don't speak Greek. I don't understand this. But that's not really the point, right? What's happening here is this very tedious stuff. It's tedious. It's like pages and pages and pages of just doing stuff. But the stuff itself is not actually hard. It's actually pretty straightforward. It's just that you have to do all these things, and then you have to kind of understand why you do that, right? So terminology can be scary and all those things. Peterson commitment sounds super scary and stuff, but it's not scary at all. Like it's very simple to understand. So curve points, we've been talking about this. I don't know if I even need to say this. So we just take a random number and we just, hey, here's my private key. And assuming it's sufficiently big, like if you take a number 2 when you use the private key, that's going to be pretty bad. People are doing it though, but they usually lose their money. But if you have a huge random number with 32 bytes or 256 bits, then usually that's unbreakable, basically. And you just take that number and you multiply it by the generator. Another terminology thing here, the G here, the big G, that's called the generator. It just turns some number into a curve point. So if you do this, it's actually, I don't know if I would call this multiplication, but anyway, we use the generator and the number to get a point on a curve. And this point is our public key for the private key A. So, and what we can do, and this was not obvious to me until very recently, I'm kind of slow, is that you can take 2 public keys and you can add them together, right? So if you add them together, you get a third. So the AG and BG, we add them together, right? And then we have the A and B, and we add those together. Now these 2 added together are actually the private keys for these 2 added together. So we have the private key and public key, and we can just add them together and add these together, and we have a new private key and public key, which is corresponding to both of them added together. Now you might think, well, that's great. We can do multisig. Well, no, you can't, because this is what we're doing here. Like when we do a verification, we don't have the private key. What we have is an equation which we can multiply by g, and if we do that, we get the public key-ish thing, which we can use to verify that something matched up. We've seen it with the Schnorr signature, with the Schnorr identity protocol, and we're going to see it again here because I'm bringing it up too. But anyway, so we can also subtract public keys together, or private keys, and this is exactly the same. So we can do map on these things. So one more terminology I want to bring up before we talk about zero knowledge proofs is nums numbers. So it just means nothing up my sleeve. It means it's a number that I created and I don't know anything about it. That's all it means. So usually the way you do this is you create a random number, kind of like you would make a new private key. You make it the x coordinate of a curve, and then you can get the y coordinate because you know the curve, and that works half the time. Because sometimes it's not on the curve, which is, then you just make a new random number and try again. Anyway, so there's nothing up my sleeve. That means I don't know, for example, I don't know the x here. I don't know that number, and I prove it to you by saying that I'm just taking the x coordinate is just the hash of my name is Kalle or something. Because you obviously don't know the private key that corresponds to that. Anyway, so there's two things. I mentioned this earlier. I said something about inner product argument. So dot product, inner product, same thing. They're written differently in different places. The way I've seen them written are the two at the top here, like A and dot in the center, B. Another way I've seen them written, and this is in the bulletproof paper, is within brackets. So all it means is that you have A, B here. You have two vectors. You take the first entry in the first vector, multiply it by the first entry in the second vector, and then you add that to the second entry times the second entry, and so on. And you could be adding these up, as you see at the bottom here. This is the dot product. So if you have two vectors of scalars, and you take the dot product of these two, you're going to get a scalar. You're not going to get a vector. There's also something called a Hadamard product. I don't know how to pronounce that, but it's an A with a ring instead of a dot. And instead of taking them and summing them together, you don't do the summation part. So you just have the first times the second as the first entry, the second times the second as the second entry, and so on, as a vector. We're going to use this later on, but it's just there's just these two. If you remember these two, that's helpful. Yeah, A with a dot, or the A with brackets, AB with brackets, is the dot product, and the other one is the Hadamard product. Okay, so we have value that's secret, and we want to hide it. So we start by saying X is our secret value. I'm just going to actually make a random one here. Oops. Okay. And now we have a public key for this secret value. If you want to, we can do that. That's our public key. You can also set the coordinates for this if you want to. Those are those. I'm going to actually do. That's too much. Okay. So, like I said before, G is the generator. In Bitcoin, there's only one generator, usually. And it's the one that we use to turn a private key into public key. But in bulletproofs, we actually have a ton of generators. We're going to have a bunch of them. And the point with the generators is that everyone knows them, and they are numbers, which means that you can't know the underlying value that created them. So I denote generators with capital letters, usually like here. And you also have a vector of generators, the capital H, no, the bold H here. So yeah, they're trivial to create. You just set some random value to the x value, or actually you set some defined value to the x value, and you have them. So I can actually show you, if I do this, I can show you, wait. That's how you, well, that's actually kind of ugly, but yeah. You just take a point of, so point, it takes an x value, chart_x is just the chart_x function, g is the generator, plus here is concatenation. It's not the double this because that's OR. And just take some, I'm just going to take one here to show you something. Or two, on the curve. So sometimes this don't work. Just try another number. I have this, which is list of all the valid ones. Well, valid first 20 something. Anyway, so right, the coordinate for this value, and then we use x plus r as the point, like that. And since we can do math and arithmetic on these points and get the same public side, we can use this to prove that we know x. And often what happens is that we use different generators. So instead of using g for both r and x, we use h for like hiding generator for the r value, and we use the regular generator for the x value or some other generator. In this case, h and g are both known to everyone. So, for example, here, and this again, the reason I'm mentioning this convoluted example is because this actually shows up later. It shows up later, and it looks scary, but all it's doing there, and there you have it. You can use those two to hide. The commitment does not show anything about the value. That's perfectly hiding. Some things can be partially hiding and stuff, but and binding is I make a commitment to a value, and then later on I decide, wait, no, I didn't mean head, I meant tails. So if I can change my head to tails without changing my commitment, then my commitment is not binding. So it's binding only if I can't change my secret after revealing the commitment. So hiding and binding, and it has been proven that you cannot have a commitment scheme that is perfectly hiding and perfectly binding. That's pretty sad, but we get pretty close. But we're going to look a little bit at how that might work soon. But so there's a correlation here with zero knowledge proofs, and I mean, you saw briefly John Newberry talk about how you can prove zero knowledge proofs and how there's three criteria. And so the hiding and binding properties kind of match up to to two of these criteria. So the hiding property matches up to the zero knowledgeness, and the binding with the knowledge someness. Okay, so we're going to start generalizing 1 plus 2 equals 3 here. Start slow, we'll start simple. So what we have here is we have variables, we have operators, we have relations. And well, first things first, like if this is a commitment, I handed you this as a commitment, then it would be perfectly binding because I can't suddenly change any of these because you see all of them. You know 1, 2, and 3. And it's also, but it's completely not hiding. It's not hiding at all because you know the secret. So this is not very good for private keys. So we could do this if you want, but this is actually perfectly hiding. I think it's very nearly perfectly hiding anyway. The problem is, of course, that it's completely unbinding. I can set x to whatever I want. I can set it to 1 or 2 or 3 or 4, head, tails, whatever I want, and it will still be valid. So it's not binding, right? If I do this, we're back to square one. It's perfectly binding again, but it's also not hiding because you just solve for x and you have x is 1, right? This is interesting, but it's not really helpful at all because you don't know either of these values, so you can't really do anything with them. And we can keep going like this. So for example, in this case, we can derive it. Okay, so a is b minus 1. Okay, that's not very helpful here. We can just say something plus something is something. We can go even more abstract. But first, I want to see this one example. If I say that I have something, but I don't know what it is, but I add it to something else, and then I minus, and I take something third away from it, and I claim that this is 0, and I commit that this is 0, then this is actually useful. Even if I don't know anything about these values, the 3 values, if I can do this, I can also say that the first 2 values equal the second value. That's pretty close to a confidential transaction, right? Like I can hide the value here, maybe. So if I say that the inputs, all of the inputs on the left-hand side, if you add them together, and you take all of the outputs on the right-hand side, then, well, even without knowing anything about the values, I know that I'm not overspending. I'm not spending more than I have, right? So that's useful. There's a problem, though. Can anyone see the problem here? What's that? Yeah, exactly. Yeah. So I could say that -1 plus -1 equals, -2, and then I can create money. Or -1 plus 1 equals 0, and I can create money. So we don't have a range check here. We don't know if we're overflowing or being negative. Actually, we can't really be negative here because these are all absolute values. But we can do things like -1 being equal to the p value, I think it is, or m value. I don't remember. But so, anyways, that basically becomes a -1 in this case. So we could do negative values to fool the viewer. So we can't. That's not enough for range proof. I'm going more into generalizing. I'm generalizing. We don't even know what the operator here is, and we have vectorized the values. So now we can do any amount of values, n values. We can do a vector of these. Anyway, so let's look at a commitment that works, and it's nearly perfect. It's nearly perfect. So if you haven't already, then why talk about this for so long? But anyway, so we have Petersen commitments, and they are very useful because they are information theoretically hiding and binding under the discrete logarithm assumption. So you heard about the discrete logarithm assumption earlier. It's a very good assumption to make because if someone would break that, they would steal all my Bitcoins and yours and everyone else's. So as long as everyone has their Bitcoin, we can probably be pretty sure that these are this assumption works. It's a big bounty at this point. So I'm only going to do this under elliptic curve stuff. You can do Petersen commitment without elliptic curves, but I don't even know how that works. I only know about the elliptic curves. So what we have is we have the 2 generators, G and H. G is the actual generator, and H is the hiding generator. We have R, which is our random value. We just make that up whenever we want to make a commitment. And then we have our value V. And this is like a private key or something. And we have a commitment, which we call capital C. So Petersen commitment, C is RH plus VG. That's it. Petersen commitments. Scary, right? Look, there's like 1, 2, 3, 4, 5 things in there. And an equal sign, and a plus. Like, geez. Anyway, so yeah, this is not very hard, as you can see. Yeah, I'm actually telling you what they are. But Anyway, so yeah, so generators, I'm just going to recap here because I've been talking for a while. Generators are predefined, nums, public, and commitments, they hide and or bind, it should be bind actually, some other value. So in Bitcoin, the public key, capital P, is a commitment to X, the private key. We don't usually say that, but that is the case. So with Peer-to-Peer commitments, there's something interesting here. There's a homomorphism, which means that, like the example here, you have a function and you take x plus y inside of it, or you take the function with x plus the function with y, and you actually get the same result. That's additive homomorphism. So Peter-to-Peer commitments have additive homomorphism. You can see R1, A1, and plus R2, the commitment of R2, A2. It's just, as you see here, you just get R1 plus R2 times H plus A1 plus H2 times G, which is exactly the same as just commitment to both of them together. So this is an interesting thing to have in mind. All right, I don't actually know these guys. But they seem appropriate for what I'm telling you now. And this is, so we have, if you dramatize zero-knowledge proofs a little, to make them a little more interesting and more child-friendly, we have 5 characters, heroes and villains. So P is a prover. Some people call her Peggy for some reason. Anyway, she proves that she knows stuff, right? So she's a good person, usually. And then we have V, the verifier. He's like the cop who makes sure that the prover does what they do, right? And we have E, the extractor, who's actually a torturer. Not as child-friendly as I was hoping, but the extractor basically makes P tell stuff, tell secrets. And sometimes this is called emulator. I don't know if there's a distinction between those two, but anyway. We have the simulator, finally, who's also a bad guy, just like the emulator, extractor, sorry. And the simulator is a conjurer of tricks, is a bold liar, and they trick the verifier in various ways. And then there's Oracle, no stuff. I will not write these in these fancy mathcal / ways. I will just write them as capital PDSO. But I will use them with non-italic to separate them from like public key stuff. Anyway, so we talked about these 3 criteria. I'm talking about them again. Completeness means that an honest prover must succeed in convincing the verifier. Right, okay. We'll talk a little more about this. We're actually going to go through a few examples. So this is the one that makes the least sense, I think, right now. But we also have something called zero knowledgeness, which means that no one learns anything. The verifier must learn nothing about the secret from the proof. Are you awake? 2 people are awake. Good. Okay, I'll keep going until you guys fall asleep. All right. Okay, so I think I've said this a couple of times now, but this is not hard. It's just tedious. There's lots of like terminology and new things, lots of things. So here's a transcript. The transcript is just a list of stuff that the prover and verifier tell each other. Verifier sends B first, and then prover sending A. No. First prover sends A, and then B, in that order, right? You saw this with John Newberry's slides. If you were asleep then, if you're awake then, you can sleep now. This is a simple example of a zero-knowledge proof scheme. And I didn't even know this was a zero-knowledge proof scheme until I read it. But so we have a secret X, we have a commitment Q, which is XG, and we have a transcript, which is capital RES. So the prover sends R, which is just the public value of the K value. And K is just random. And then V sends back E, which is also a random value. And then P sends K plus EX and calls it S. And then V verifies. So when you're verifying something, I write it as equals question mark. Sometimes question mark is above the equal sign. Depends on if I'm using LaTeX or not. So anyway, sounds good, right? I need to have Q as well. This is the public key. Right. So everyone knows Q. I'm now sending, as you can see, first thing I send, prover sends R, capital R. The verifier already knows capital Q, because that's my public key. So I send R. Now V creates E. Important that V creates key after I send R. And says that to me. So now prover has sent E over back to me. And now the prover calculates S, which is K plus E times X. That's S, all right? And now V verifies. So if everything is working according to plan, S times G should give the same value as R plus EQ. Okay, let's try it. S times G and R plus EQ. Look at that. That worked. So Schnorr is not broken. That's good. Side note here, not super important. This is an example of a Sigma protocol. And you're like, oh shit, that's super complicated. I can never understand that, right? Well, a Sigma protocol, you know the Sigma sign? It looks like a backwards E. Anyway, so okay. So we talked about three features, completeness and zero-knowledgeness and knowledge soundness. So we're going to look at Schnorr signatures a little more in detail. And we're going to first look at completeness, right? So you have a prover, and I'm not even going to read this, just read it. Yeah, I don't understand what I mean either. So instead, I'm going to show you an example. If you don't have the password yet, ask friends. This. Ha. Transcript goes like this. Okay. Maybe I won't show you this retarded transcript. Okay, wow. It's a red transcript. Okay. Send you R, send you E, and send you Z, where X is the hash of Z. Okay, so I'm proving knowledge about X here. Okay, that's important. This is the private key. This is this is the secret I'm trying to prove. And so, but this zero knowledge proof requires you to send me the pre-image of X as a hash value. So we need to have the Z value, which is equal to the inverted hash of Z, right? But we can't do that. Well, actually, X, sorry. But we can't do that, because if we could do that, we could break everything, right? So we don't actually know how to, we can't prove anything. We can't prove, even if we have X, we can't prove it. This may not be all of it, but this is a part of soundness, the criteria. If we can't prove that we have X, even though we have X, the zero knowledge proof is broken, right? Okay. So now it's the simulator. I was talking about the simulator. They were the conjurer of tricks, right? Now they're going to take control over the verifier's execution environment, and they're going to be doing stuff with it. So what they do is they're going to do time leaps. So they're going to create this transcript, and they're going to create it out of order. Okay? EQ. And then they set the transcript to these three values and say, hey, there you go. And the verifier goes through, and it just takes SG and takes R plus EQ, and it worked, right? But the simulator does not actually know the secret. But they can still make a proof for it, right? So let's see how that works. Let's make a random value. Let's make another random value. Let's make, oops. Right, so we have S, and we have to have Q. Sorry, so Q is some point. Yeah, so obviously the reason why we could fool the verifier here is because we created a transcript out of order. Yeah. Oh, sorry, yeah. Yeah. Zero knowledge and what? Sound, you mean knowledge soundness or completeness? You mean this one? I was talking. Yeah. Yeah, exactly. Yeah, yeah, that's a very good question, right? So how can you do that? Anyone know? Like any ideas? How did the simulator fool the verifier that they knew the secret, even though they don't know the secret? Because I don't know what x is here. Because q is just the SHA-256 of hello world set as the x coordinate. It's just some x coordinate random. Well, so the reason here is, and I was mentioning this before, if you go back to the transcript slide, so I'm saying at the bottom, I'm saying the order is crucial. Right? You have to do this in order. You have to send the first one from the prover, and then the second one sends from the verifier. And if you don't do this in order, then you can fool someone. It doesn't matter. And also, what this also means is that if someone is observing after a proof has been made, if someone looks at the proof that the prover and verifier created, it means nothing. Because the prover and verifier can be working together to fool you into thinking it's a real proof. So the only way to know for sure is by seeing this in order. You have to do A, then B, then C. If you do this in any order, your proof is pointless. So here, the simulator created S and E first, right? So that's out of order. They should come last. They came first. And then you can just solve R, like capital R. You can just solve it. And the point here is, what you may be seeing here is that I don't know what K is either. You know, the random value I use to create R normally. I'm supposed to use R equals K times G. I have no idea what R is in this situation. But I can fool you into thinking I do because all you know is R. You don't know X. So I can just say, hey, here's R to K value. So yeah, the order here is what matters. But so if you think about this for a moment, so okay, by changing the order of the transcript, I think to make a fake one was to change the order. It follows that you don't learn anything about the secret. Okay? All I did was change the order, and I proved to you something that was not the case. Changing the order does not create information, right? There's a slight note about the distribution here. Don't really have to care about that. But there's a caveat, so don't run out and start creating zero knowledge proofs without knowing that part. But anyway, okay, so zero knowledgeness and completeness. Any questions about zero knowledgeness or completeness? Okay. So last one, knowledge soundness. This is kind of complementary to zero knowledgeness in a way. So now we have another evil guy, the torturer, remember, extractor. He now takes control of the prover and tortures him in various ways, or her. Peggy, right? Yeah. So what we do here, so the idea here is we manipulate the prover somehow. So what we do is we kind of debug the prover. We can go back, we can go forward, we can kind of restart, and we can repeat stuff and copy states and stuff. So we look at the Schnorr Identity Protocol case again. Right, so, okay. Question, does P actually prove that he knows X, or could he somehow fake it? We have RES, and S is K plus EX, and R is KG. And extractor runs the prover first point only. So he gets R. The extractor now has R. He has one R. And the extractor now saves the state. It saves it like a game. like a video game. You just save, and then you can reload later. He saves, and then he runs to the end. So he gives a random value E1, and he gets back a random. He gets back an S1. Right? He gave a random value. He got back S. This is one run. He does this 2 times. So he gets a second one. But what he does is he now, instead of going from the beginning, he loads after twice. I can get your private key. Isn't that great? So why? How did I get your private key? Just me. Any ideas? Why I got it? How can I get it? Like this is normal, right? It's okay. So here's a hint. It's the most common error that people do in cryptography. Yeah. Yeah, exactly. I reused the nonce. Yeah. Because I reused the nonce k, because I had the same k here, I can just solve for the private key. If k1 and k2 were different, we would have more unknowns than we have equations. And we would keep having more and more and more. If I did this 100 times, I would have 100 different k's, so I would just have more unknowns all the time. So yeah. So this proves knowledge soundness for the Schnorr identity protocol. Is everyone okay with that? Does that work with you? Like, it's pretty convincing, right? I mean, if I can get the private key from you somehow, just by going back and forth like this, it must mean that you have the private key. Right? How much time do you have? 5 minutes? Okay. Yeah, okay. Maybe we can do. I can continue this while we're drinking. No, never mind. All right. Right. So to summarize these two, the zero knowledgeness and knowledge soundness. So I can prove the zero knowledgeness, and the way I do this is that I manipulate the verifier. I manipulate them so that they believe that I have a proof, even though I don't. And if the two proofs, the valid one and the invalid one, if they are both indistinguishable, then it follows that you have zero knowledgeness. I may be missing some sublegal there. I'm sure that someone on Slack will slap me if that is the case. And you prove knowledge soundness by changing by manipulating the prover, and we were debugging the prover, going back and doing stuff like this. And by doing that, we made them reuse the nonce, which made them give us the private key. So, and it's important to note that you cannot use a fake prover to prove knowledge, because if you try to do that here, we actually can't do that, because this verifier was doing the transcript in a different order, right? The extractor was rewinding and going forward, so that requires that you have this time linearity thing, right? Yeah, so I'm going to talk a little bit about PDC commitments in vector form. I'm going to go a little faster now because I don't have that of v values. And important to note here is that this is not, this is the dot product. I forgot to mention that, but when you have vectors together like this, it implies that there's a little dot in between. So this is the first v plus times the first g plus the second v times the second g and so on. We can go further. We won't, but we can. So g, okay, yeah, g is a vector of generators. So right. So to do this in PDC commitments, we have to create a commitment for each of these vectors. Right, so we have m vectors. That's not m numbers, that's m number lists. So it's kind of like a matrix. And so we create m Cs, m commitments. The first R plus the first X times the G. The generator here is the same. The H is always the same. We just keep iterating the X's. So we created these commitments. Question, have we revealed anything by showing them to the world? The answer is no. These commitments are still perfectly hiding, but they're not perfectly binding, only under the discrete logarithm assumption. So, okay, so we get a little hairier now. So we have a zero-knowledge protocol for vectors, which starts with a C0. And this is just a random vector. A commitment to a random vector, sorry. And then we have, as normal, the random E, and then we have two things from the prover, a vector and another scalar. And as you can see, prover sends Z0, verifier sends E, prover sends Z and S. So it's a Sigma protocol example. You can Google that if you want. So anyway, so the way we do this is we create Z and S in this fashion. We just, remember E, the random value that the verifier sent us? We use that, and we just take it, and we take it to the power of I. So for the first one, we actually don't use it at all. And the second one, we use E, so an E squared, and so on. And we do this on both Z and S. So we get a vector, and we get a scalar. And as you note here, we're actually iterating from 0 here, because remember we had C0, which is accompanied by the complementary X0 vector, which is just a random vector, and the R0, which is just a random number. And so the verifier just does, it just takes a sum, EI times CI, and he checks that is SH plus CG. Okay? Is it? Well, we can look a little. We can take the right-hand side, and we can just do this. And we say, yeah, okay. That works, right? Yeah, that's kind of like how it goes. Like you're like, yeah, that's right, okay. And you keep doing this like over and over. So this is actually, this is actually a completeness proof, because C0, it sets it to SH plus ZG minus this sum here. And you just make Z and S up as you want. It looks really like weird and complicated, but I mean, he's just making up shit, and it works, right? It's just like simply just slap it together, and there you go. And zero knowledge is it's all about just slapping things together or making things so hard that you get tired, right? What I mean by that is I'm talking about the discrete log assumption, where it's like you cannot prove this is possible, or you cannot prove that this is the case, but you can prove that this is so hard that it would be easier to just try to find Satoshi's private keys, right? Which works, I think. It's good enough. Anyway, I'll talk a little bit about lonely sums, then I'm going to call it. I would have liked to talk about inner product stuff. But I don't think that's going to happen, because I think you're all getting pukey at me now. Anyway, so knowledge soundness. Now, remember what we want to try to do here. We want to prove that the prover has these vectors, the x vectors, right? And how do we do that? Well, we make them give us all of those vectors. And we do that by just running back and forth and just debugging the prover with a C0 that is the same. So by having a non-random C0 or the same C0, we could just do this enough times, and eventually we have more equations than we have. It's not hard at all. It's you just do this stuff, and you're like, okay, I'll do that 100 million times, and then okay, well, you know. Yeah. So I'm not going to talk about this. If you really have not tired of me yet, which would surprise me a lot, then you can ping me. We can sit down and I can show you about the inner product zero knowledge proof. That's kind of the only really complicated thing that is left. There's, well, sort of. But if you know about the inner product zero knowledge proofs, you can probably just sit down with the paper and especially if you have wax wings paper, you'll be like, you know, it's not as hard as it looks, and understand all of it. So yeah.
So because these are theoretically hiding but not theoretically binding,
Yeah.
does that mean that in a scenario where a lot of computers exist, you won't be able to know, basically you'll be able to inflate?
Well, so it's binding in the same manner that a private key is binding. So if I can come up with a new private key corresponding to your public key, which is possible, it's very hard, then if I can do that reliably, then we have a lot of big other problems to solve before we even care about that. I think the entire system is going to break.
I understand, but I just mean in relation to like this construction.
Yeah.
What we're saying is that
Right.
binding essentially applies to being able to hold the commitment on a value.
Yeah.
So if it's broken, if DLT is broken, then you can inflate on the network.
Well, it's only so okay. So first of all, you cannot have perfect binding and perfect hiding.
Right.
Right. You can only have one of them. And Peterson commitments are like they're perfectly binding under the discrete logarithm assumption, which is exactly the same assumption that you have for private keys and public keys.
Right.
So if we can break that assumption, then everyone loses their money anyway. Even, you know, I mean, you're kind of breaking more stuff than just this. Inflation is not going to be your biggest problem.
Right.
I think. I may be wrong. Someone on Slack will slap me if I'm wrong, I'm sure.
Thanks.
Okay.
Oh, one other question.
Yeah.
Are we building, so do these vectors essentially map to the commitments in the range proof? So like each commitment would be like the ring signature over a particular value?
We don't use ring signatures. So what we do instead is we use the inner product to create a circuit that tells us, one, that our values are not overflowing, they're within a certain amount, and two, that they don't exceed each other, right? And we do that by, we do that in a very, very obscure and, yeah, as you see, I have not gotten to the end of my slides, as you can see here. So, okay, so range proof here. So what we do is we actually, it looks like a hack. It probably is a hack. It could probably be more elegant. I don't know. But so what you do is you take the value, and then you create a vector where you say 1 or 0, right? So so you turn it into the log 2. Sorry, not the decimal, the binary value, and then you just take one. Each one is the binary value of that a bit in the number. And then you create this other vector, which is called bolded 2 here. It just means 1, 2, 4, 8, 16, 32. So you get this representation of the number as a vector of 1s and 0s. And then what you prove is you prove 1, that it's only 1s and 0s. It's not minus 1s or 2s or anything. And you prove 2, that it's more than and less than a certain value. Actually, I don't think you prove that it's more than a certain value. I think you just prove it's less than a certain value. You can go through it if you want, but I don't think I have time anymore. I think they're going to throw me out of this. So,
Thank you.
all right.
Okay, so let's take the last break of the day. Let's take another 10 minutes, and then after that we'll go through the last 3 sessions. 今日の最後の10分の休憩を取ります。その後は最後の3つのセッションをやりましょう。 Coffees is also still available, and the remaining lunch boxes you can also bring it home with you if you want. コーヒーもありますんで、あとは、残ってるの弁当も持って帰っても大丈夫ということで、ぜひ。
Don't forget there is coffee for everybody who is jet lagging.
いい ?OK。次、日本語のセッションになります。デイジーラボの中川と申します。今回は M of N のスレッショルドシグネチャーユージングシュノアっていうので、要は、N 人の中から M 人が出てきて、証明するっていうようなセッションになります。で、このセッションの目的なんですけど、大きく3つあります。秘密の共有の方法っていうのをまず、1位に決めるためには、稽古の点があれば、十分ですよっていうようなのを使ってやります。で、じゃあその3つの点があったらどうやったら多項式を求めますかっていうと、このラグランジュの補完っていうような、この下の式を使って、導くことができます。でこれだとちょっと分かんないんで、例として K が3の場合を、考えてみますと。でそうすると、要はこの fx の a0 プラス hx プラス a2 の x の2乗っていうような式が求められるようになればいいと。でラグランジュの公式使うと一番下のような fx っていうようなものが生まれますと、考えてみますと。でそうすると、x1 を入れてみると赤い部分のところで、全部0になっちゃって右の部分が全部なくなっちゃいますと。で y1 の部分の方を見てみると上の分母と分子が同じなのでこれ1になって、結局 y1 になりますよねっていうようなことで、同じようなことが、x2 にも x3 にも言えるので、3点を通るねっていうことが分かりますと。で、秘密分散の方法なんですけど、シャミアンの秘密分散法の場合には、1人のディーラーがいて N 人のプレイヤーがいますと。でその N 人の中から M 人が集まれば、秘密を再構築できるよっていうような、ことをします。で、ちょっとずれちゃってますけど、ディーラーは秘密値を S っていうのを作ります。で S っていうのは A0 になります。それからディーラーはランダム値を、M-1 個分作ります。で、さっきの多項式を生成します。でこれに対して、各プレイヤーに x1 から x1y1 っていうのを、M 人に N 人に全部送りますと。で、M 個あればさっきの公式から、秘密が出ますと。でラグランジュの公式が上のになるんですけど、秘密鍵はさっき設定したように0なので、F の0を入れた時が、要は秘密になりますよというので、下のような式になりますと。で M 人のプレイヤーが集まればこれを使って、復元することが S を復元することができますということです。でちょっともう分かりづらいんで演習ということで、ちょっと僕、作ったのでこのページを開いてみてくださいと。はい、こんなのになります。で計算得意な方は、ここの97っていうのをクリックすると素数が3つぐらいになるので、大きめの素数にして計算してみてください。これでよくわかんないけど秘密鍵決めますと。で秘密鍵を決めて、あとはランダムの値を決めますと。そうすると下のようにダラダラダラとできます。なのでディーラーはさっきの多項式を利用して、プレイヤーの1には1の60、プレイヤーの2には2の22みたいな感じで、数値を送りますと。でそうすると、P1 と P2 から P5 までができて、でこれらが何でもいいんで、これ3オブ5なんで5人に対して3人が集まればできるようになっているので3人適当に選びますと。でこれ123にすると計算が楽なんで多分123でまずやってみた方がいいと思いますけど、そうするとこんなような式が出ます。これさっきのラグランジュの公式が出ていると思うので、これを計算してみましょうということでちょっとやってみてみましょうということですね。多分123にするとここのところが3、ここがマイナス3で、43になると。で43になるっていうと、この辺の式が同じになりますっていうので、ちょっとやってみてください。やってみて、で3やめて4にしても結局ここは43のままだったり、135にしても 43になります。ここの S の式がマイナスになっちゃった人は97というかこの素数を足し込んでプラスになるまでやってみてください。で逆に97を超えちゃった人は97からこう引いてみて、97を引いて、97以下になるようにすると同じような答えが出ると思います。というものなんですけど、問題なのは要はプレイヤーN 人が、もらった XY っていうのは、正しいのか正しくないのかっていうのは、実際プレイヤーの方には分からないのでこれ検証する必要が、出てくるというのが、問題になりますと。で、要は検証可能な秘密分散法っていうようなことが必要になります。で、それから、もう一つポイントとしてさっきは、ディーラーが1人いたのでディーラーは S を知ってる状態になっちゃうんですけど実際に例えば、N 人で共有する鍵を作って M 人で再構築するってなった時に、N 人の誰かが、要は秘密鍵を知っていたらそれはあんまり意味がなくて要はランダムに秘密鍵を作んなきゃいけない N 人がランダムな秘密鍵を作って自分の秘密鍵を作ってみんなに、渡す。それから、その後の M 人が集まったらそれぞれのものがあるので、それを再構築できるっていうような形になります。はい、でこれは楕円曲線上の問題で、基本的に大文字は楕円曲線上の点だと考えてください。で小文字は、単なるスカラーだと思ってください。ただちょっとプレイヤーは、PI としてちょっと大文字になっちゃいますけどそういうのをしますと。で各プレイヤーが、さっきと同じように乱数を作りますと。でそれを今回乱数が2つ出てきますと。で、それを、fx と f'(x) っていうような多項式を作ってそれぞれを各プレイヤーに送信しますと。で、各プレイヤーは、その後、コミットメントっていうのを作ります。さっき、彼がやったバレットブルーフのところにも出てきたんですけどそれと同じようなもんですね。でコミットメントを使ってみんなにブロードキャストしますと。で各プレイヤーはその受けたコミットメントを検証しますと。このさっきのバレットブルーで出てきたのと同じ式ですね。S と G に対してコミットメントを足し込むと、答えが出てくるよってこれが合ってるかどうかっていうことで、要は、僕らがもらった S の I とか S っていうか、みんなが配った、XY の座標が合ってるかどうかってことが分かりますと。で、各プレイヤーとしては、これが分かったら今度は、G 側ですね。今こっち側のこの A の G 側の方を渡してこれらをブロードキャストします。そうすると同じように今度は S' じゃなくて S だけを検証してこれがあったものが合っていれば S は正しいものだということが分かりますと。はい、ちょっと図にするとこんな感じになりますと。要は、多項式作ります。これに G をかけたものと F' に H をかけたもので、このようなコミットメントが、いっぱい出てきますと。でコミットメントと自分がもらったものをこう足し合わせて検証することができます。でこれができたら、合ってるので今度はこっち側の上の部分だけ渡してもらって S が正しいかどうかを検証するっていうような流れになりますと。鍵っていうのはどうするかっていうとさっき出したこの A0 っていうのの一番最初のこの部分ですね。これが秘密なのでこれを全部足し合わせたのがランダムな秘密鍵に対する公開鍵っていうような感じになります。で M 人のプレイヤーがいれば、さっきと同じ、公式を使って、求めれば、秘密鍵が復元できますと。はい、ということでこれもちょっと演習をやってみます。2番目のタブ開いてもらって、今回 G で H、検証です。プレイヤー1はプレイヤー2とプレイヤー3に、値を送って プレイヤーにはプレイヤー1とプレイヤー3に値を送ってっていうような感じになります。で、各プレイヤーがそれを渡した後に各プレイヤーはコミットメントを渡します。コミットメントは、要はこんな式で出すんですけど、実際はこのポイントしか送らないので、他の人たちはここに何を足し込んだかっていうのはよく分かりません。で、こんな感じで、こっち側が要はもらった S と S' の計算で、こっち側はブロードキャストしたポイントですね、を足し込んだのが、これが合ってるかどうかっていうのをやりますと。で、ちょっとやってみますと、1だと簡単なんでやりますと、例えば、P1 が、プレイヤー1がプレイヤー3からもらったものが正しいかどうかを調べるときっていうのは、これが96と96、H は2倍なので、96の3倍。これ3倍誰か288で、これが、3と30を出せばいいので、すると多分これとこれが合っているので、合ってますねっていう感じでコミットメントが確かめることができますと。で、このコミットメントを確かめたら次に、今度は A の方だけの、ものを、みんなに、配布しますと。で、これも同じように、正しいかどうかを確かめますと。で、これで正しかったら、公開鍵の P みたいなのができてて、これに対して送りますと。で、これを、要は秘密鍵を作って復元するときには、要は3人のうちの2人が必要ということで、2なので、92っていうのが実際にこのポイントになるかどうかを32バイトの大きな数になるので、もっと複雑な形になります、複雑な数字になりますけど、やってることは同じということになります。はい、で、この S の IJ と A の IJ というのを共有する手順をVSS と呼ぶことにしますと。はい、で、シュノアの署名に対して、今度はこれを適用していきますという話になります。で、シュノアは、ここで扱うのはちょっと単純なシュノアにします。で、基本的に秘密鍵を S、乱数値を R としたときに、単純に、署名は R とハッシュ値の S っていうような形にします。で、検証自体は、署名値の G をかけたのと、ランダム R と、メッセージと、P を足し合わせたものがイコールであれば、シュノアを割っているというような、ちょっとこういう形のシュノアにします。で、ちょっと、VIP シュノアとかで書いてあるのとはちょっと違うんですけど、同じようなものなのでこれでいきます。はい。で、鍵の生成はさっきの VSS の方法を使って、共有しますと。なので、公開鍵は全部足したものになっていきますと。で、M 人のプレイヤーが、証明書を発行しますと。はい。で、要は、シュノアの場合って、この R っていうのが問題で、R も同じように VSS を使って共有します。なので R に関しては、これは M of M の共有と考えていただければいいです。で、R ができますと。で、各プレイヤーは、証明書を送りますと。で、 どんな証明書を送るかっていうと、自分たちが持っているところの、シノアの計算をして、各プレイヤーに送りますと。で、各プレイヤーはそれが正しいかどうかを検証しますと。これ複雑に見えてますけど、要はやってることは乱数の部分と、証明書の部分をやってて、ここはシノアの署名でやってみて、これが合ってるかどうかっていうのを検証します。そうすると、各プレイヤーが出した証明書っていうのが多分同じなので、この証明書を、さっきと同じような、ラグランジュの公式に当てはめれば、証明値が求まります。それから乱数も求まります。なのでこれが、いわゆる証明になりますと。で、ちょっとこれもやってみます。はい、今度はもう多分全部できていると思います。で、こんな感じでさっきと同じように H は単なる2倍にしてあります。で、キーももうみんなに渡されているとします。で、この書いかけに対して送っています。なのでこのうちの2人を選ぶと、ランダム数が配られて、それぞれのランダム数がこれになります。証明っていうのが、1と2が出しているのが、1302と1995になります。で、それ自体が正しいかどうかを調べることができて、で、これが正しいですねってことが分かって、で、証明値を出しますと。で、証明値はさっきのラグランジュまんま出します。で、これ単純に3分の2なんで、これ簡単な式になってきて、で、これを出すと証明値が609っていう形になりますと。で、609のになって、これが合っているかどうかを調べてみましょうということで、調べてみますと。609がR と H の P。ハッシュ値は単純な3にしているので、これで合ってると思う。合ってますね。はい。これで合ってますということですね。で、これなんですけど、実際こうなってて、今回このランダム数は、P1 と P2 が作ったランダム数なので、これを P2 外して P3 にすると、ランダム数が変わるので、証明値が変わります。はい。ということで、検証ができましたということですね。はい。で、まとめになります。秘密の共有の方法っていうのは、シャミアの秘密分散法を使って、共有していきます。で、これだけだとちょっと問題がいろいろあるので、ランダムな秘密鍵ということで、それぞれが同じようにディーラーになったりプレイヤーになったりすることで、要は共有していきますので、検証可能な方法としてはコミットメントっていう方法を使って検証可能な状態にするので、正しいことが分かった状態で秘密をそれぞれが保持できるというようなことになります。で、シノアへの適用 A はどうするかっていうと、秘密値とランダム値にこの VSS っていうのを使ってそれぞれ共有することで、基本的には署名値というか、秘密が分からないんだけど署名ができるというような状態になって、シノアにうまく適用できるということが分かりますと。で、参考はこの辺のものを見ていただければと思います。ということで、ありがとうございました。
Okay, now I'm going to talk about Taproot and Graftroot. A couple ideas that have come into the space in the past year for scripting languages or the replacements thereof. So the background here is that every script type that I talked about previously, and people have talked about, are distinct. They look different, so from a kind of privacy perspective, that's pretty bad. You watermark, you fingerprint yourself all the time. This makes things like fungibility worse. Bitcoin isn't worth 1 Bitcoin anymore. You have censorship risk and other issues. Also, if you're doing any kind of complex scripting, often you are paying for these contingencies that are never used. So in certain scripts you'll have, the thing you normally do, but once in a while you might need to use another clause in the script, and you have to pay for that every single time. So these kind of interesting cases that actually exist in real life, you have kind of two cases. You have the cooperative case where everyone behaves, signs, and then updates the state. So in the M of N Schnorr case, which was just talked about, this case will just look like one signature for one public key. But then you might have some complex script as a backup measure. Say you expect maybe that a threshold is not enough and too many signers go offline, and after, say, a year or something, you want to recover the funds with a smaller threshold. With that, in a normal script, you'd have to say, even with M of N Schnorr, you'd have checksig, else, CSV, back off for, however many blocks, and then another public key. You also have things like time locks, hash preimages, and what I just mentioned is the telescoping multisig case. What if we could instead optimize for the first case if we believed it would be far more common? And then the participants would not have to pay for the contingency case, which also might be a much larger script. So in the Lightning Network case, the typical case is the 2 of 2 multisig, which with Schnorr could look like 1. With the kind of expensive scripts that punish the bad behavior, or the unilateral closings, which means if your cosigner in the channel goes offline, you have to spend more money to get your money back, and that's not great. For telescoping multisigs, you have N of M multisig with a timeout to a small multisig, as I said. So those are a couple cases. So there's been an idea where, for privacy reasons, for example, you could have a Merkleized abstract syntax tree. Sorry, I didn't put it out there. Basically, have a Merkle tree that is an exclusive, is a logical OR. So you expose one of the leaves of this tree, and that leaf would commit to a script. And as long as you satisfy that script, you can spend the funds. So, for example, you could have a Merkle tree of 2 with 2 leaves, and the left branch would be the common case, say. So everyone spends case, the M of N Schnorr case, say. And then the right side would be some complex script you never really want to show off unless it really happens. So you'd only have to spend the funds to reveal the script and lose the privacy when this contingency is stumbled upon. You can also just have a subtree with many possible conditions attached. For this to be privacy kind of preserving, everyone by default would have to do such a thing. Everyone would have to commit to a mass tree, even if you don't have a contingency. Most wallets today don't, right? It's simple single signature or maybe a multisig. So everyone would have to pay this cost, which is kind of unlikely. The one nice thing about it is there's no interactivity required on setup time. But one of the key insights was a way of adding these contingencies without without increasing cost or reducing privacy. So there's this concept called pay-to-contract, which I'm not sure has been talked about today, so I'll go through it. It's a method of committing to a specific message within a public key. So address, you could take the queue, make a normal address out of it, and pay to it, and then you have provably bound it to this key P plus this message. So this message could be something like, in the element sidechain specifically, for example, it's committing to an address that will be your address in the sidechain. So consensus doesn't care about this in Bitcoin, but you're provably committing to this. And only one binding is possible at a time. And the trick here is that if you can sign for P and have the message that's being the hash, and having the script that's being hashed in, then you know how to spend the queue, and if and only if. So we can commit to this contingency that we talked about inside of Bitcoin while maintaining just having this queue point be like a pay-to-pubkey style address. And so the key verifiable secret sharing scheme. Because every single participant in that scheme knows how to compute their own section of P, their own shards of P, and they also know the hash of P appended to script. It's not a secret among this federation, so they are able to all sign for this. Verifiers have no knowledge of this on the typical case. In the typical case, they will just sign for Q, and it will look like a normal pay-to-pubkey output being spent. The contingency is reveal P, the original pub key, reveal the script itself, and then verifiers are able to take P, add it with the hash of P appended to script through generator G, and they can verify that that adds up to Q. It's the same thing. And then you basically recurse into the script and treat that as some sort of contingency script. Could be a Bitcoin script, could be anything else. And again, there's no setup time interactivity required. You could have a policy up front for every single output having the same contingency script, and you don't have to interact for that. Any questions? Okay. So the downside here is that the binding to the script here only means there can only be one contingency. Or if you want additional contingencies, you have to embed it in a verticalized abstract syntax tree amassed to have further revelations. But again, for each contingency that you have, it increases the, it should be n log n there, the cost. So there might be another way to solve this, which was kind of a revival of an old idea of delegation. So delegation is the method of you encumber. So basically the typical setup would be you'd have this multi-sig people doing the Schnorr kind of multi-sig for Q. So at creation time, all parties would delegate to another script by using their shards of Q to sign a message that redelegates it, right? So the hash of Q appended to script 2, where script 2 is actually the new encumbrance, this new secret encumbrance. And you can do as many as you like, right? So you could sign as many scripts as you like independently, and as long as one of those is valid and attached to the transaction and fulfilled, then the transaction is valid. So this does require that these signatures have to be stored, right? Before we had this non-interactivity that as long as you know your partner's public key shards ahead of time, you can do this without extra storage or interactivity. But now you have to have all participants send each other signatures and store them indefinitely. so those kind of the two major two ways have been thought of to increase the contingency sets without reducing privacy. And this kind of dovetails with some stuff that John Newberry was talking about. It's kind of these two schools of thought that you might, scripting languages, if you add expressibility, it also tends to lower privacy, as every new script is a privacy leak. It's a fingerprint risk. And also, if not carefully designed, it increases the denial of service and consensus risk, where the complexity means that every node has to compute the answer just as fast as you'd hope, and also agree with other nodes, especially alternative implementations. And the other way is having less script or no script at all. So for the Taproot and Graftroot cases, you could just not have a script at all. Instead, have an actual template that says, hash lock key or CSV key, and it's not interpreted as script, it's just a templated thing that people understand. They optimize for the common cases, and then you include more privacy by default, but also it's lower flexibility, as well as lower risk. And here's some background on some of the tools that people have done. The original paper for the pay-to-contract paper, at the bottom, a little tool you can play with, the contract hash functionality, and then the emails. So that's all I got. Thank you. Questions?
So I guess it's an unintentional last break while Eric is coming here. Okay. じゃあエリック来る前にまでに、休憩取ります。
Eric had to step out for a couple of minutes. He should be back shortly. Let's give him 10 minutes. Meanwhile, get maybe coffee and water. Let's do a break.
Hello. How's that? Got two, listening? Hello? 1, 2, 3. Just the volume on that. If I can see it. Volume up. No, don't do that. Don't do that. Okay. Everybody back? The break over? Just stay here. You ready? Okay. Welcome back. I'm glad I made it. Crap, blurry slides. Sorry. I'm Eric. I don't have a bio slide, but it's easy to find information about me. This last presentation of the day is going to be a little different. This is Dev++, but my opinion, the first thing that developers need to know is what they're building. So I'm going to talk a little bit about theory behind Bitcoin. Oh, cool. And I'm going to introduce a new term that I just cooked up because there wasn't a term that made me happy. So I'm going to define something called crypto dynamics by the end of this, which I consider a subset of crypto economics. And here we are. So what's crypto? I just pulled this out of Wikipedia, chopped it up a little bit. Cryptocurrency is a money that uses strong cryptography to secure financial transactions, control the creation of additional units, and verify the transfer of units. And those, I thought that was actually, aside from the fact that it uses cryptography, and this is important when it comes to defining what Bitcoin is and how it's secured. Okay, so we put those together. You know, again, I just cooked this up because I didn't have the right word for it. Forces that generally, again, this is paraphrasing the previous slide, basically previous to forces that generally secure financial transactions, and specifically by doing that by controlling the definition of units. In other words, controlling the definition of the money. You know, can somebody just cook up some more? And controlling the transfer of units. In other words, you know, who gets mined, right? What transactions can get confirmed? Okay, so to do that, I'm going to go through. So I've talked that I give quite a bit. I'm going to try to stay on time, but this is a good amount of material, and I'm going to speak quickly because I always do. But I do have a lot more text on some of the later slides than I normally would because I wanted you know, non-native English speakers to get the benefit of the translations and have some content with them. So I'll try not to just read those, but there's some good text for the takeaway. So what is Bitcoin? Conceptually, what are we dealing with? And these are my definitions. Sometimes they're a little bit different than what you might be used to, but this is really just for the sake of this discussion. You don't have to take it away if you don't want to. But I consider Bitcoin a class of cryptocurrencies, given the previous definitions of those. And Bitcoin is a transaction confirmation market. Okay? You have miners and merchants. Merchants are people who sell stuff to other people for Bitcoin, in my definition. Okay? Doesn't mean they're selling dollars or shoes or gas or drugs or, you know, gambling or whatever. They're merchants. They're the ones who validate the coin they receive in a way that actually matters. Miners are the ones that sell confirmations, right? They get paid fees for confirming transactions. The merchants pay them for it. So if you think about the direct analogy in the Visa network, right? Visa's the miners, they sell confirmations. The merchants are the ones that want the transactions confirmed. And you might think as technical people, well, it's really the people who buy the stuff that send the transactions off to get confirmed. So I ask you, if you submit a Visa, if you go and, you know, make a Visa charge at the gas station or something, do you care if it gets confirmed? No, you don't want it to be confirmed, right? The gas station guy wants it to be confirmed. The merchant is the only one who cares. So don't be confused by the technical flow of things. Think about the conceptual model, right? This is what Bitcoin is. It's a market for confirming transactions. And for some reason, it has better characteristics in some ways than other markets for confirming transactions, right? Okay, so this class of cryptocurrencies shares a common security model, again, by my definition of what we're talking about in terms of Bitcoin. So I would consider Litecoin a Bitcoin, right? It's got some minor parameter changes, a few tweaks here and there, but there's nothing in the white paper that doesn't describe Litecoin. So that's what I'm talking about here, okay? Not BTC specifically.
And those concepts are defined by the white paper, even if they're not so clearly spelled out. And so that's what I'm going to try to do, is help more clearly spell them out so that when we're looking at whether something is a Bitcoin or not, conceptually, does it follow that model? How do we know? And what are the limits? What really matters? Does the block size the thing that matters? Is it every specific rule? What actually is securing the money to the extent that it matters? And so we're going to talk about the dynamic principles, the things that are actually securing the money. Okay, and that's that. So why is it a better money than other monies? In some cases, it's clearly not. If you don't have a network, it's not a very good money. But in some cases, it's got significant value. So the value proposition of Bitcoin is that it gets the state out of the money as much as possible, right? All the costs that go into other monies that Bitcoin eliminates are all the result of being free from state control, okay? Nation states, governments, what have you. So I just call this the money tax, right? There's direct taxation that comes out of being able to control and see the flow of money. There's monetary inflation, which we should all be familiar with. There's foreign exchange controls, regulatory controls, and surveillance, which again goes back to being able to enforce taxes, ultimately. So these are all costs of using monies that Bitcoin tries to reduce. It can't eliminate the state, tax, or banking, but it makes the money better by getting the state out of it as much as possible. In the end, that may result in more transparent taxation. People may be able to see how they're being taxed, but that's not really the important aspect. We're just analyzing what makes it valuable. So the state, in our technical terminology, the state attacks every market. Every market is under the attack by the state. It's a third party injecting itself between other two parties to tax. So through control, extract tax from the market, where the market here is the previous slide, right? The transaction confirmation market. Need a water. Try not to spill that on your laptop there. Okay, so we have the definition of what we're talking about in terms of Bitcoin, the reason it's valuable, and then we can talk about, well, how does it actually secure itself? Well, I usually have a longer talk on this, but I'm just going to go through what I consider the 4 phases of Bitcoin to kind of give you a sense of the security model. These are not necessary phases. It does not ever have to go out of the honeymoon phase, which it is in right now. But these are the phases that the security model anticipates, right? It's why things work the way they work. Bitcoin anticipates that some person with some power might want to actually make it illegal, so then it can still operate, right? We think it can withstand that. And then we also think that somebody might try to 51% attack it, right? They might try to control transaction flow, and we have to ask ourselves, well, how do we defend against that? How does the system do that? But those are the things it's designed to do. So quickly, 4 phases. Honeymoon phase. It's not having enough of an impact on taxation for the state to care. And I'll talk more about the generalization of the state later because it's always a question. But they don't care. So, yeah, there's regulatory controls that apply to all financial stuff that kind of apply to Bitcoin, but it's not under attack by the state, not really anywhere. So we're in this honeymoon phase where we can do what we want and it all looks secure until it doesn't. So when the state realizes, hey, this thing actually works, it's actually taking tax revenue out from the state. We don't want that. We don't want to lose the ability to tax what we can see outside of the money. We don't want to lose what we call monetary policy, the ability to create new money, spend it ourselves, right? Don't want to lose that. Well, what's the easiest thing to do when you're the state? Pass a law, right? Now, some people will say, well, laws are hard to pass because voters will reject that. Well, I say that's the status quo. That's where we are already without Bitcoin, right? Voters already have the power, the pitchforks, whatever they need to go and make a good money or to prevent the state from messing with their gold, whatever. The theory is that doesn't work, okay? So we have to be able to do that without permission. Bitcoin doesn't require permission. So state steps in and says, it's now illegal. You can't use it. And then I'll show you what the alternative will be that they'll propose, but that's the easiest thing. Stroke of a pen, boom, it's illegal. Now, what happens? Everybody that's using Bitcoin, meaning mining and merchanting, is a money launderer, a criminal money launderer, right? Everything to do with Bitcoin all of a sudden became black market. That could happen with a stroke of a few pens around the world. Doesn't have to happen everywhere. That's not really the important thing. So we go into this black market phase, but guess what? Just like all black markets, it just continues to do its thing, just different places. So about 1/3 of the world's economy is black market, and Bitcoin can presumably serve a good part of that. And maybe it stays there forever, right? People just keep using it, and you know, state says it's illegal, but it's just kind of like, you know, gambling in some parts of the world, prostitution, drugs, you know, labor, whatever. But if it's really still making an impact, and we want to stomp this thing out, it's the drug war, right? We're going to really, you know, send in the Blackhawks and clean out Colombia or something. What do? Well, they pull up one of these videos and they go, what should we do? We should compete. We should compete with the miners. Because by competing with the miners, they can get control of transaction ordering. We'll talk about why here in a second. Okay, so let's say the state's winning this 51% attack, and just nobody, you know, the market can't overpower it. What happens? Surrender. The market gives up. There's no more Bitcoin, basically, right? Or state's losing, market's winning. What happens? State probably has to give up at some point. So I'll explain why. You raise your fee, you raise your fee, you raise your fee. State's not taking those fees. But the fees are rising for other miners who will take them. So once they rise high enough, more hash power comes online. State now is competing with higher hash rate. It has to raise its hash rate without getting the additional fees. Okay, there's a delta there between the fees the state's taking and the fees the black market miners are taking. We call that a fee premium, and that fee premium is what's securing Bitcoin against censorship. If people are willing to pay enough, the black market will come on, the free market miners will come on and mine those transactions. The state, in order to counter that, will have to raise taxes, an external source of revenue to subsidize its mining, which is operating now at a loss. It can do that. How much? Who knows? These aren't predictable things. Like, you know, what is the cost of censoring Bitcoin? It's not a knowable thing. It has to do with how willing the state is to do it and how willing the market is to get transactions confirmed. Okay? It doesn't have anything to do with total hash rate. Right? Think about those. So this is why it's important for developers to think about the security model, because it's not what you think. All right, so I said earlier, you know, the feds step in. I call this FedCoin. It's this abstraction that the perfect, smallest perfect minor modifications to Bitcoin to make it a government-friendly currency, right? So what do you need? Those two things on the very first slides we were talking about that the cryptocurrencies are doing. They're securing definition of the money and transaction confirmation, right? Ordering or the ability to transact, right? So those are the two things, obviously, that the state wants control of. They want monetary policy, and they want to be able to have visibility or approval authority over all transactions. So how would they do that? Simplest model is I step in, I say, okay, if you mine any transaction, it has to be signed by the Fed or, you know, some international body. So if it is, it's good, white market transaction. If it's not, it's money laundering. Okay, so now I have pushed Bitcoin transaction ordering into the black market while giving an alternative which seems perfectly safe and reasonable to everybody. So some people go one way, some people say, no, I'm going to keep mine in the black market transactions. The other thing they want is to be able to create new money, right? Obviously, that's what we're trying to stop. So how do they do that? Well, they force every merchant to accept a new rule which says if it's signed by me, the Fed or whatever, then it can be new money. You just issue new money, no, an inflation bug, right? So with those two changes, it becomes the perfect money. So the merchants are defending against the definition of the money. They're the only ones that can validate in a way that matters. They can reject selling something to somebody if the money doesn't meet their criteria. That's economic force. Miners are the only ones that can control transaction ordering, therefore censorship. And the way that's going to be secured, as I described before, is by the black market stepping in and saying, I'm just going to mine them, right? So you have these two sides of the market, merchants and miners, which, like in every other market, are independently securing their own stuff, right? If you go to Starbucks, they secure the store, the coffee, the registers, all that stuff. That's not your problem. You show up with some money and you secure your money, right? That's not their problem. And then you trade, and that trade is mutually beneficial. Trade's a positive sum game. Both parties are better off after the trade because otherwise they wouldn't have done it, right? They wanted to. It's voluntary, so it's by definition better than what came before. So this free market, you know, is now being attacked by the tax man who steps in and wants to do this stuff. So that's exactly how Bitcoin works. In other words, the threat model is not the miners and the merchants attacking each other. That's a nonsensical proposition. When anybody says, well, yeah, that can't happen in Bitcoin because they'd be destroying their own market and there'd be no incentive. Exactly. That's not the threat, right? It's not why it's secure. It's just not the threat. The threat is the state. Okay, so did I cover all this? Yeah. Okay, so here we get to the thing I think is not really new, but more clearly defined. And when I say not really new, it's not new to me because these are things I've talked about and written about before in different ways, but probably new to most people in the room because, I don't know, I think differently. Okay, so the principles of cryptodynamics that I put down I call risk sharing, energy sinking, and power regulating. This is the stuff, this is the cool part. Okay, so security is by its very nature a human problem. It's not a machine problem. So think about anything you might want to secure. Your house. Okay, so is your house secure because you lock the doors? Because you have a dog? No. Smash the windows, go in, take all your stuff. No problem. Shoot the dog, give him some meat, whatever. It's not securing your house. What's securing your house is your neighbors or yourself when you're in the house. If you don't have any neighbors, imagine what your house is going to look like when you come back from vacation, right? Maybe not in Japan, but in the rest of the world. So it's people that provide security. So people say, well, guns would provide security. No, you know, guns just laid on the ground. They don't do anything. You got to pick them up and aim them at somebody and use them, take a risk. So all forms of security, firewall. We got a firewall wherever, back here somewhere. How does that, you know, how is that a human thing? Because without humans, somebody just walk in and unplug it, right? Everything is secured by people. So Bitcoin is no different, and I really want to emphasize that. Technology people, which I'm one of, you know, I have a long background in technology, but I'm also a security person, you know, an economics person, a lot of things, tend to forget this, like, or never knew it. Like, security does not come from cryptography. Cryptography is a tool like a gun that has to be used. So in Bitcoin, who's providing that security? Okay? Okay, people must act. So this action that I'm talking about is why I call it dynamic. People actually have to do things, right? It's not like dynamic math or crypto, it's people moving. Okay, so we only expect people to act in an economically rational manner, self-interest. If we don't, then we have a failed system, at least from an economic standpoint. Okay, so these are the forces that secure Bitcoin. I'm going to talk about each of these. These are the ones that have more words on the slides. Okay, 3 principles, and then a summary slide, and then I'll be done. I'm not even keeping track of time, so tell me where I am. Okay, the risk-sharing principle. These are all topics that are in the Bitcoin base library repo under basically a book called Crypto Economics. Risk-sharing principle is one of these principles. So Bitcoin requires people to merchant and mine despite it being illegal. If they don't do that, it just doesn't exist, right? Imagine step in, sign a law, it's illegal, boom. Everybody says, oh, fuck, it's illegal, I'm not doing it anymore. It's done. There's no more Bitcoin. So the assumption is people will actually go and break the law, or there's no security, there's nothing, right? It's all gone. So you can argue that, well, they'll never pass that law, and I'll say, great, so we never left the honeymoon phase. Fine. But that's not what Bitcoin is designed to do, is kind of stay in this phase where nobody ever cares because it's not having enough impact. Or it sits in this phase because it's a politically secured money, right? The vote is what secures the money, which is also the status quo, which obviously hasn't worked. So security rests entirely on them resisting through covert operation. This is a very important principle when it comes to the technology. If you're resisting the state and you're not hiding, what are you? You're lucky or you're in jail, right? You know, or you can break out the pitchforks and fight out in the open. But basically, Bitcoin assumes that people will violate the prohibition and do it covertly. Well, how do they do it covertly? What if it, you know, what if it requires massive machinery and all this stuff, right? This is where we start talking about decentralization. This is why decentralization matters, because you can't hide if you're running a major operation, right? So hiding is necessary to the security model. Anonymity is necessary to the security model. The ability to get the data without having to provide identity or get permission, right? Try to get access to all the accounting information in the Federal Reserve. Try to submit a transaction through the Federal Reserve system, right? Without permission. You can't do it. So Bitcoin doesn't require any permission, and it requires that people be able to operate at small scale for the sole purpose of being able to operate covertly. Okay, so I covered those. Miners and merchants. So every individual person in these 2 categories of the market are defining their own level of acceptable risk. Okay, so you know, if people don't want to take any risk, there's just not going to be many people using the money. But this is not something that the software can determine, right? And it's not something you can predict based on some kind of economic foresight. It's just people's willingness to resist. It's like all prices. They're in people's minds, their preferences. Okay, so in doing this, each secures their own piece of the market against the state's attack. And if a cryptocurrency does not allow risk sharing, it cannot be secure. In other words, if one entity is ultimately taking all the risk and it gets 2 life sentences, it's not a secure system. So that's principle number 1. Bitcoin operates, each principle builds on the other. Nothing can happen unless people can hide, operate in secret, and therefore share all the risk of running the system. Okay, energy sinking. This is more cool. So I'll just start I guess I'll read these. A person must be given authority to order transactions. I see one of those transaction ordering guys in the back of the room there. All right, so how does that happen in Bitcoin? How does some person get the authority to choose the transactions? They get lucky, right? They run a bunch of stuff and they get lucky. Oh, I get to do it today, right? So it's anonymous, it's probabilistic, but it is a person being given authority temporarily to order the transactions. And due to risk sharing, this requires anonymous proof of authority. How do you get anonymous proof of authority? Well, Satoshi said we'll use proof of work. That sounds like a great idea. The great thing about proof of work is it's basically anonymous. Anybody can presumably come up with energy, and you don't need permission to, or any identity to get the data that you need to mine. Okay, so these anonymous systems could be either internal or external. This is my terminology. So internal to the coin means all the information about who's the authority is derivable from what's in the chain, essentially, right? External means it's completely independent of the chain who gets authority. It's just being injected into the money. So proof of work is obviously that external source of energy coming in. Proof of stake is the internal source of information that's already there. And there really are no, somebody tell me if you can think of something else, but I don't see any other ways to do it. There's an internal system and there's an external system. You can call them what you want, but it's really staking and energy. Because everything external is going to reduce to energy. One of my favorite, examples, and again, this is why developers need to know these principles, because you could go off and. So I won't, that's a fun topic. I won't go into more detail on that, but 2 ways to do it. Well, why doesn't stake work? People come up with all kinds of reasons why stake doesn't work. My reason is a little different. A censor with controlling state cannot be unseated. There's no way to get them out. Once they have controlling stake, they own the money. It's over. Right? You can go create a new money, right? Start over, keep shrinking your monies, but that's why it's not crypto-dynamically secure. A censor with majority work can be unseated. Just add more work. You can always add more work to the system. And then what I described earlier about the free market paying not order by sinking energy, principle number 2. Of course, it has to be, risk sharing still applies. That hasn't changed. So third principle. These are like Newton's laws of Bitcoin. In my mind, I hope Bitcoin becomes that important. Power regulating principle. I've already described this, so just kind of summarize this. A sustained 51% attack can censor all transactions. It's totally doable. As a censor ignores unauthorized transactions, their fees rise. Rising fees compensate other miners, increasing overall hash rate. To maintain majority hash rate, the censor must subsidize through taxation. This results in competition between taxation and the fee premium, the offsetting fees, not the total fees, because remember, if everybody's taking the same transactions, the censor's making the same amount of money as the market, right? So how can the market get the black market transactions mined? They have to pay extra, and the extra is what makes the difference. So this is a good example of another error that developers have made, thinking that an inflation-only coin can be secure. It's not just a simple kind of arbitrary choice, maybe a little more inflation, a little more fees. Inflation does nothing to secure, and by inflation I mean the block subsidy, right? It does nothing to secure against censorship. Absolutely zero. And if you had a whole coin based on inflation, like perpetual inflation and no fees, it would be absolutely insecure. And that's what this principle says. If it does not regulate power with fees, it cannot be secure. So why is that? Again, if you only had inflation, you have no way to identify and pay more for the transactions that are getting rejected. So every miner is taking the same transactions, presumably only the legal ones, because there's no more money in taking the illegal ones. Right? So the black market miner and the white market miner are the same miner. They're making the same money, and there's no way to create a difference between them to overpower the censor. That's why inflation does not work. Okay, my last slide, just some insights. Crypto dynamic security defines Bitcoin, in my terminology, right? That's what I mean by crypto. It's what defines it, the concept of Bitcoin. If you take those three principles and you apply them with good engineering, you essentially have Bitcoin, right? You might get the blocks too big, and you might not be able to be able to operate covertly. You might get the interval too frequent, and there's all kinds of things you can get wrong. But if you don't do these things, it's not Bitcoin. If you do them, it may or may not be a good Bitcoin. Utility, which means the usefulness of the money, is not assured. It's not guaranteed because of some crypto we wrote, right? The utility is that the benefit of the money must exceed the cost of using it. So if the fees rise high enough because the censor's willing to tax enough, the money won't be useful. People will just stop using it because it's not better than the state money. So when we talk about engineering, what does that mean? Like, we're trying to make Bitcoin better. There's a whole room full of people here and recognize a bunch of people that, they're out there trying to make Bitcoin better. And in many ways, all the things they're doing are making Bitcoin better by these principles, and sometimes they're not. So if you can make it more private, be able to operate more efficiently at small scale, what does that mean? Now there's less risk in doing it and less cost in doing it, which means that the black market can be more effective against that one big centralized player, right? Which means the fee premium is lower. Therefore, it's a better money than it would have been otherwise. So these things that improve privacy, reduce scale of necessary operation, contribute to the security of Bitcoin. So when we talk about some of the things we're doing with also decoupling inputs and outputs, that's also allowing people to operate privately, more privately. So merchanting will be less costly so that people will actually do it when it's not okay to do it. If it's okay to do it, it stays in the honeymoon phase, so what? It doesn't matter. Okay, that's all I got.
Hi, I come from Spain, and at least in Spain we're getting a lot of fellow nerds that are leaving from Venezuela. And in Venezuela, the government is going, if not against Bitcoin, at least against the miners, the local ones. You think that governments like those in Venezuela can be used as kind of a lab test to understand the direction, or they lack enough power to be relevant?
So I'm gonna take your question and move it into a bigger context, because there's some more questions that'll come out of that, but it's all kind of connected. So when I give this talk, people will inevitably in the back of their minds just that's always the case. It's going to be the case, right? So if only Venezuela creates a black market, right? The white market's huge. It doesn't really matter to Bitcoin. It might matter in Venezuela, but we're talking about system level security. How does this money actually stay functional? So imagine we get to a drug war scale banning of Bitcoin. Like this is all money laundering. We got FedCoin. It's perfectly safe. You should do that. But if you do this, you're money laundering. To me, that's such. If Bitcoin is effective, that's inevitable, right? So when that happens, people say, well, maybe Moscow will say it's all cool, or Iran or something, right? Yeah, but they're already money launderers, right? I mean, by the definitions we deal with today in the financial system, they're already cut out of the finance. It's no different, right? So yes, that will happen, but all it means is that they're just a big piece of land with a lot of black market in it. If they can't muster enough hash rate, then it doesn't make any difference. So it's always the black market will succeed to the extent it wants to and takes the risk. But Bitcoin is unique. It's not like gold analogy is like very good in some ways and just horrible in other ways. How do you attack gold from a single point on the planet? You can put up one mine and attack Bitcoin all around the planet. That's a weakness, and people have to recognize that. So it doesn't really matter where the white and the black market is. It just matters that there's enough state, right, enough taxpayer money to muster, to raise the fee level to the point where people won't use the money anymore. So I hope that actually answered your question.
What are your thoughts on holding multiple different currencies as a way to spread the risk? I believe most of us here are pretty maximalists, but do you think that would be a way to say, okay, I do not hold all my wealth in one currency, so
Okay, so I'll just restate, because it wasn't on the mic. What do I think about holding multiple currencies as a defense against state-level attacks on, say, one or the biggest one, right? Well, if the currencies are very similar, and they are independent of the state, they are bitcoins, which means they could be secure, then Thier's law applies, which means that it's more costly to use the crappier ones, so everybody ends up using the better one. It's the inverse of Gresham's law, right? And it's more costly because you have a higher exchange cost, because not everybody's taking the smaller one. That's why it's smaller. The more people that take a money, the more valuable the money is, the more useful it is. So it's like having European money versus the euro, right? I remember going country to country in Europe and changing my money everywhere. It gets really expensive. So that's kind of what you're talking about. Okay, well, we can use all these different monies to try to have a better money, but in the end, all you're doing is raising the cost of the money. So it's still kind of the same problem. Thier's law says it'll all collapse into one. If that one gets attacked and goes away, well, you can just create it again, right? You can do it again, but the smaller monies will be weaker, and they'll be more costly to use. So it's not really solving the problem. Personally, I think experimenting with different approaches is great. Somebody can, if somebody can be the Einstein to my Newton here and find a new concept, that would be awesome. It really would. But has anybody seen a new concept, a truly new concept that actually works after hearing how I describe these concepts? I haven't. Right.
I don't know. I like the way you weigh the balance between transaction fees and the tax that the state can get. So there's an equilibrium point, right?
Right.
Which beyond that, you will incentivize miners to join.
Right. So to restate, you like the power balancing principle, which is that there's a balance between not the fees, but the fee premium and the tax, right? And yeah, the market can just push the state out if it wants to, because miners will be incented and they'll mine, or they won't, and the fees will go up. Up to the point where they're infinite and you can't get anything through, right? That nobody mines anymore.
And a similar way, there could be a point in which the price or the cost for multiple units is what you're paying for minimizing the risk.
Sorry, I didn't get that.
The way you're spreading the risk has a cost.
Right.
Maybe there's a point in which that cost is just the same cost compared to different units, and you say, okay, it's the minimum cost price.
Right. It turns out to be the same thing, right? You got to transact across a bunch of currencies with exchange costs, or you have one currency and you have all the costs bundled up in there. But yeah, it all comes down to cost. I mean, it's like I was having a discussion with somebody just yesterday, and he's like, okay, is it hash power that secures the history or against censorship? I'm like, well, hash power doesn't secure against anything. It's money. It's again, principles of action. Somebody has to spend some money for Bitcoin to be secure. They have to pay a miner to go do the mining. That's a payment, and whether it comes through inflation or not, it's somebody actually has to pay it. And remember, inflation doesn't actually guard against censorship, right? Inflation is designed to distribute the coins, and it does pay miners, but it doesn't pay miners in a way that guards against censorship, because the censor gets paid the exact same amount as the non-censor. There's no differential. You can't,
Is internal stake or external work? As I understand, you mean proof of stake and proof of work, right?
Right. When I
Is there any difference with internal or external, in your opinion?
The difference between internal and external proof is that internal proof cannot be secure, and external proof can be, right? And the reason for that is because internal proof, nothing new can be brought into the system. So once the censor has enough of whatever it takes, whether it's 50% of some stake or any other complicated formula, once they've achieved enough, there's not going to be any way to get them out. And of course, if the system's anonymous and decentralized, small operation like it has to be secure, because that's the first principle, then there's no way to know whether the state's doing it, right? They're just as anonymous as everybody else. So you can't identify them and kind of kick them out. You could reset your coin and throw a bunch of coins out and try to start over, but every time you do that, your coin just gets less valuable. It gets smaller. That's what's wrong with I call it the proof of work fallacy, the idea that you could just hard fork your way out of 51% attacks. Every time you do that, who gets screwed? Who's the miner going out of business? It's the big miner or the small miners? Who's got better margins? There's a premium for being big, right? So you make more money, you have more capital, you can build more stuff, afterwards. And I've actually put this to big miners. They say, yeah, we just retool. Right? Small miners are like they're completely out of business. So you just you do that, which is not great, but you just keep shrinking your money. Right? And I wrote that up. There's a number of I'm getting the hook here, I think. And there's a number of explanations for why that is. But yeah, Tom. All right.
Okay. Once more, thanks to Eric for this wonderful talk. And with that, congratulations, you've completed day 1 of Dev++. And yeah, I hope we'll see you again tomorrow. Does Anton have any announcements or anything? Okay, so thank you for coming, and hopefully we see you again tomorrow. So we start again at 8:30. 本日来ていただいてありがとうございました。1日目がやっと無事に終了いたします。また明日、8時半から頑張りましょう。よろしくお願いします。
Sorry about giving you a scare there. Sorry about the